All righty.
All right, so let's go ahead and get started. At least I think it's time, right? Yeah. So let's go ahead and get started. For those of you who don't know me, I'm Dave Tucker. I'm the host of this organization, along with Dr. Nana Zhou, who can wave at us. She's the one running the show for the most part, and she's going to go over all the kind of rules for the sessions today. But today we'll have 3 sessions. The first one on microgrids that will be chaired by Mr. Rick Lank, who is the CEO of Resilient Power Works, and then later on, after this session, we'll have a session on hybrid power systems, and then at the end of the day, we'll have one on dynamics of hybrid power systems. So it should be an exciting day. So with that, I'll turn it over to you, Nana, so that you can go ahead and go through the mandatory slides we need to do at the beginning of every session.
Can you hear me?
Yes.
Yep, we can.
So Dave, if I have a problem with my audio again, then you can just pick up from where I leave. So I see some audience first time to join the LEAP today. I didn't see you yesterday, so I will go through some more slides. LEAP is a 5-day event. Today is the second day. You are welcome and invited to all 5 days events. If you go to our website, you can see the detailed agenda. We have 14 sessions altogether. You can find the sessions that interest you the most and participate. And every day we have different links. You can find all those in the website and also in the agenda. In each session, we may have keynote speaker, or maybe in another session it's panel discussion. So it's different from session to session. Again, you can just choose the ones you like. And also between sessions, we have breaks. Usually we have breakout rooms available. If you want to stay longer to continue the discussion or to talk to some colleagues that you haven't met for a long time, feel free to stay in one breakout room. And this is what I have to say at the beginning of each session, that this is considered as an open to public workshop, which means all the information in your presentation, in your discussion, must be publicly available before this meeting. So to make sure that you don't release any sensitive or unpublished data in this presentation. And second is that the entire workshop will be recorded so that we can develop a technical technical report after the workshop, which will be shared with all the audience when it's available. And we suggest you to turn on your camera while you are talking, either giving a presentation or asking questions, joining the discussion. And because we have many participants, so we suggest you to mute yourself except when you are talking. And we encourage you to interact with the presenters. You can join the discussion after the presentation, or during the presentation, you can post your questions in chat. The session chair will pick up the question and ask the presenters, or we would, try to answer all the questions at the discussion part. I think that's all from me. The stage is yours, Rick.
Well, okay, Rick, just one quick comment.
Sure.
So if you did send the presentations to us, if we have your presentations, we've posted them online, and so they're considered to be published. So it is public information. Just put a heads up. That's why we asked for all the presentations. So, okay,
Sure,
all right, Rick.
Sure.
Take it away. I'll let you get started. Yep. Yes, sir.
Sure. All right, everybody. I can't thank you enough for showing up on this morning. Dave and I have had the chance to work together for the last 4 years or so on some of the technologies which we'll be discussing in my little pitch in the beginning. But I just, for the sake of making this a very interactive session with, time constraints, of course, we're going to be doing some polling questions. And the way it works is that we've presented enough questions with multiple answers, you can only answer one of them. And Brian just put them up on the screen. There'll be two at the very beginning, and then there'll be a sequence of about 4 or 5 more as we go along. Now, the important part here to keep in mind is I have to keep the banter going with you guys while the questions are being answered. We cannot post a slide or slide deck during the time while this is running. I see it has a time limit of 2 minutes. So what I'm going to do with that 2 minutes to get everyone to know each other a little bit is give you a preview of the talks that you will hear. Of course, between each talk, I will introduce everybody individually, but here's basically what you're going to learn today or hear from us today. The first workshop will be, or talk will be mine. Hopefully I'll be joined from time to time by Dr. Tucker. It's going to be all about hydrogen-powered hybrid microgrids and advanced power controls. And just so you know, our little outfit, Resilient Power Works, mostly works in the front-end engineering and design and commercialization sphere for new technologies. The second presentation will be Steve Steffel, formerly of Pepco Holdings Incorporated, or PHI, now Quanta Technology. Steve has years of experience of working with new technologies in an existing distribution network. He retired just last year, but he is very active with Quanta Technologies to this day. The next will be joined by a fellow whom I was recently introduced to by the name of Colonel Matt Baker. He is from Massachusetts, where his firm is located, which is, what is it called? Typhoon Hill, excuse me. And they specialize in microgrid and critical power controls. The next up will be Ronnie Clark, I believe with two of his compatriots, Alexander Coleman and hopefully Joe Walsh, that they'll be talking about mastering reliability and resiliency, a New York City case study in microgrid design. And last but certainly not least will be optimizing microgrid designs for the behind-the-meter client with CEO Jeff Oxnam of American Microgrid Solutions. Looks like we just timed out, and that's great. Brian, do I just get to read out loud the responses that we have so far?
I shared them on
screen?
I shared them with everyone, so you should be able to see the folks that did answer. The majority of them were from academia. There was
And research.
6 from microgrid developers.
Okay.
4 from Europe and 14 from North America.
Great. Okay. So we do have somebody from the European community. That's fantastic. All right. Well, what we're going to do, I guess, Brian, if you could just roll on to my first slide, we can take it from there.
Let me give that to Nana. I think there she goes.
Okay. Great. I was lucky enough to give this particular presentation just 2 weeks ago downtown at the National Harbor for Tech Connect. And there is a lot of interest, as all of you know, in hydrogen these days. And most of the research that I've learned about, including some additional funding for Nettle, is for the production of hydrogen for a processing to go for industry. The thing that's so unique and special about what Dr. Tucker and his team have created is the ability for a microgrid to produce its own hydrogen power on site. Does not have to be transported. And again, Dr. Tucker's extreme experience is with thermal storage. His background is in chemical engineering. And so his team, which includes people that are in the advanced power controls arena, they've been able to do some remarkable things with respect to how a microgrid can be extraordinarily responsive and extremely clean in its energy consumption. All right, next slide, Nana. There we go. A little tiny bit about the Nettle Lab. It's called the Hybrid Performance Lab, or HYPER. This is a photo of a part of the lab itself. It is very much its own test bed. It has virtually everything that is real hardware, with the exception of the fuel cell that they work with. As Davis told me, they would have blown up about 1,000 fuel cells in the last 10 years had they had the real thing. So it is a cyber physical model, and they are able to work with a variety of technologies and other labs to do the simulations that they require to test out the hybrid model. Now, some of the research that takes place at the hyper facility includes, of course, the advanced control methods. One of the things that Dave has been able to accomplish is an extreme turn down ratio and a very fast ramp rate for the turbines. Allows for a very nice model for low cost spinning reserves for the utility industry. They've worked extensively with fuel composition flexibility, and in terms of the fuel cells, which is one of the real loves of Dr. Tucker, they've been able to demonstrate a 7 to 10-fold increase in component lifetime, extending the life of a fuel cell from roughly 2 years to roughly 14 years. This is all something that's, I don't want to call it hypothetical, but I will say, Dave, could you just expound on how you've made that jump to know how you can extend the life to that extent of the
Okay,
component?
sure. So first I'm going to say, okay, the extensive turn down, that was accomplished by Dr. Zhang, who will be talking actually later. The fuel composition flexibility is Dr. Farida Haroon, and the tenfold increase in component lifetime, that's Professor Valentina Zakaria, who I know is on the line as well. But anyway, yes,
Okay.
they're all part of the hyper team at NETL. But anyway,
Excellent.
yeah, this is all accomplished through a combination of hardware and software. Using cyber physical models, as you mentioned, Rick, which will be discussed in detail actually on Thursday and Friday. So
Excellent. Good. So we're setting the stage for Thursday and Friday here. That's good. Alrighty, Nana, next slide, please. Okay, Dave, in just a minute, I'm going to ask you on the next slide to jump in. But the three keywords that we're dealing with for the audience takeaway is hydrogen, hybrid, and microgrids. And I want to allow Dave to talk more about the hydrogen in the next slide that we produced together. The hybrid component, let me just mention very quickly, is extraordinarily important because it does involve the solid oxide fuel cell, a natural gas turbine, which behaves more or less like I call it a bladeless wind turbine. We'll get into that later, and the natural gas reformer. Then we'll get into applications and controls. Go ahead, Nan. I'm sorry. All right, turquoise hydrogen. The design, Dave, and correct me if I'm wrong, can operate as either a blue hydrogen model, or it can, with the addition of course, solar power and a few other things like the solid oxide electrolyzer, can function as a green hydrogen producer. So take it away from there, please, Dave.
okay, so everybody, Rick is torturing me because I wasn't able to make it. He had to go through all these slides on his own. But yeah, so keeping in the spirit of, I'll try to take as little time as possible. The whole point here is that if you hybridize, if you combine a lot of these technologies, you have the potential for taking advantage of all the heat sinks and heat sources that are available in a hybrid system to generate hydrogen when you have excess electricity, or generate electricity, when you don't have enough from renewable resources. And again, I think we will actually have an opportunity to talk about this later on. But in the next session, we'll be actually talking about different cycles using all of these different components and making them work. But these are certainly concepts that we've tested out at the lab,
Right.
in ETL.
All righty. All right. Nana, next slide, please. Now, while we were at the downtown event, we did focus our attention on the advanced power controls that are required. Two components. Number one, you have those very, very advanced controls that have been worked on at the lab that is just for the unit itself, for the power producing hybrid system. Then you have another set of controls which deal with SCADA, supervisory controls, everything that interacts with the utility grid. And that takes another unique set of controls. And we're going to fuse those two together. And what Dave Tucker and I are working on is a precision power platform, or 3Ps for short. That's the area of our greatest focus right now, because in my opinion, Dr. Tucker and his team have brought the model, the hybrid model, almost to perfection. There are two areas that we'll discuss where we need additional work with the advanced power controls. One is load following, and the other one is increasing compressor efficiency. However, we are also looking at cybersecurity control elements. And just to make life more interesting, Dr. Tucker and I also are on a team called Blossom, which is looking at the different ways that blockchain technologies can help to protect the controls. We're looking at both before the meter and utility side applications for the utility industry. We're looking at a model that will allow a group of these microgrids to be networked within a distribution network for additional black start capability and a variety of other benefits to the utility, like low-cost spinning reserves. And Dr. Tucker has been able to make this model extremely scalable, as small as 100 kilowatts, all the way up to several megawatts and beyond. The limitation is largely with the solid oxide fuel cell and its costs. If we can keep those costs lower, Dave, please correct me if I'm wrong, but I believe the formula that you have told me is the solid oxide fuel cell can only needs to contribute about 15 to 17% of the total electricity. Does that sound right in the model that you've created? So in other words,
Okay,
if we had to, yeah, I'm sorry, go ahead, Dave.
So yeah, we've looked at different, doing different system analyses where we varied the size, down as low as 20% and as much as 60%.
Oh, okay. All right, good.
But
It's important because a lot of people think that the fuel cell has to contribute 100% of the power at all times. And part of the magic of the extension of life for the components is the way that the different components share, if you would, in the function of producing the total electrical package. They don't all have to contribute 100%. Also, the flexibility, this can produce blue hydrogen as just a hybrid model. It can also add renewables to the mix, and it can produce green hydrogen. Okay, go ahead. And Dave, I'm going to ask you to jump in on here too. This is a slight modification of your original slide, Dave. We just wanted to share with you the basic components in this particular diagram of this particular model of microgrid power design. You can see that it does include, if need be, the solid oxide electrolysis cell as well as the fuel cell. Dave, you can explain, if you don't mind, the internal combustion engine's role and the heat exchanger's role. Carbon capture, of course, is essential to the way this model works, especially in the green hydrogen model, if I'm not mistaken. So once again, Dave, if you wouldn't mind explaining that a little bit more for me, for us.
Sure, I will, but I hate to monopolize time in
This
workshop
is
I'm hosting, but
oh, no. This is the meat of the matter right here.
sure. So the idea is, like I said before, because we can thermally and chemically couple these different components and systems, we can take advantage of the heat flows. And the idea is in the Integrate program, which we'll be talking about tomorrow. Dr. Dave too will be going over having some of the participants from the Integrate program talk about this, but you can use elements, unutilized fuel from the fuel cell and pressurized airflow to run an IC engine that can be turned on and off for peaking demands, which greatly improves your flexibility. And it's a very low cost element to the entire system. So, and then, yeah, you do use carbon capture. That way you can use your SOEC to produce CO and hydrogen, which you can convert to liquid fuels, and then store those and then re-reform them as needed for additional power, or put those as essentially a green fuel into the transportation market.
Right. Great. Thank you, Dave. Thank you very much. Nana, please, next slide. Now, here are just a few of the key attributes of the model. And Dave, jump in anytime you wish, but there are turn down ratios achieved already, I believe, for the natural gas turbines of 90% or more. There are extremely fast ramp rates, which basically means that your natural gas turbine can behave more or less like a diesel generator and ramp up very quickly when there's a power failure on the general grid. And just to repeat what we've already talked about briefly, Dave's model shows that we can extend solid oxide fuel cell life by up to 7 times. And even though that does not diminish the upfront cost of a fuel cell, it just immensely enhances the return on investment for a utility, for example, to buy and utilize the fuel cells if they can last 7 times of what the original lifespan was. So we believe that this particular model makes an economically viable transition to a clean, hydrogen-based distribution generation future. Next slide, please, Nana. And Dave, there are just a few comments I'd like to have you make on this. This, of course, came from a different slide deck, Dave, that you, I believe, gave to a United Nations crowd. But the essential thing here that we wanted to demonstrate is that with coal, the percentage of CO2 emissions are vast. You have tons of CO2 emitted from per 1 megawatt hour of power generation on your axis to the left. And of course, as you go from coal to natural gas to a solid oxide fuel cell hybrid, like David has developed, your cycle efficiency improves enormously. The additional discussion about load following, we're not going to get into at this point, but the key thing to remember is to produce 1 megawatt hour of power, it's almost 2 tons of CO2 emission, and that drops off rapidly when you move towards a solid oxide fuel cell / natural gas hybrid model. Dave, would you like to expand on any part of that? Because I know I took it out of context of the other deck to demonstrate that.
So Dr. Bhima Sastry presented this yesterday as well in the first session.
Okay.
But yeah, you said it pretty well, right?
Okay, fine. Nana, next slide, please. All righty. Now we'll just get back to where we want to go in terms of some of the additional work at hand. First of all, just to sum up 2 things very key for other people to keep in mind as we go down the road here. The hydrogen hybrid model can work as a grid-tied producer of power. It can work on either side of the so-called meter, behind the meter for client-based work, and it can work for a utility company where and when they can own their own power generating capacity. And then they have 2 functions, and Dave, just correct me if I'm wrong, but we can design this to produce electricity only for, say, utility, or it can function as a CHP plant for private industry where people need both the heat and the electricity. Is that a safe statement? It is? Okay, that's good. You all right with that then? Thank you, Dave. Thumbs up to you too. All right, the additional research we talked about earlier it all deals with the advanced power controls. Dave has all the factors, all the components, all the testing done to allow this to function, his HHM to function as a load following power producing plant, which would be phenomenal. It would work, for example, in a distribution network, and it could reduce peak load shaving requirements on behalf of the utility, have a very efficient use of electricity. It cannot do it at this point, but we're working towards that one particular objective. Also, in order to increase the compressor efficiency and the overall efficiency and safety of the model, Dave had originally designed a little something called the blue button. That would be a manual stopgap measure if there were either visual or vibrational or sound experiences with this system that would signal that it was getting too close to the stall line, which has some dire consequences. Anyway, we've been working towards automating the process of the so-called blue button, so a human operator does not have to be next to the power plant to either listen for a sound of stress or feel a vibration that signals stress. And we are preparing a proposal for the National Science Foundation to advance that particular component of compressor efficiency through controls. All right, now the next one. As we briefly discussed, we have to have both dynamic and supervisory controls, and anything that would help to protect the whole system from being hacked. But at the center of all this, to interface with the utility, we are also working on the SCADA or supervisory controls that would link the hybrid model with any other form of generation that might be on the distribution network. Okay, next slide, Nana. And right here was sort of a highlight of everything. We do feature here with a smart microgrid design, all parts and components integrated by the triple P, if you would. There's chemical storage, and we have fuel conversion for high energy density. I'm just reading right from the screen. Dave, if you want or add anything at any time, please do. There's thermal storage, which is, again, the key to the whole design, something that Dave has been working on for years, for both low-grade heat loads and high-grade heat for electric transients. There's the hybrid system for dynamics and transient load conditions. And when you have dispatchable or intermittent, assets, this can help to integrate all those many components together. The essentials of the HHM is that it acts as for the base load generation that you require, and then you can add the more intermittent elements to the overall system. All right, go ahead, Nana, please. This will be my transitional slide. I'm going to give you one more slide that we tacked on the end. And just and before we go to Steve Steffel, is that I'd like to introduce, with Brian's help, the very next of the polling questions. That one does deal with basically which of these fuels will contribute the most carbon grid by the year 2035, which is at the heart of our whole discussion here today. So I see that we have it up on the screen now. We'll take about 2 minutes to complete for everybody. And the one thing I will discuss while we're waiting for this to be completed is that the next slide that you'll see is from 1956, and it deals with the early days of distributed generation. And I know it'll be very a nice segue for Steve Steffel. And Steve, of course, has been with Pepco Holdings, and I just wanted to read what his last job entailed. He was the manager of distributed energy resources planning and analytics for 10 years for PHI, which now is owned, of course, by Exelon. And Steve, again, is working with Quanta Technology. But going back to our slide from 1956, you'll see that it deals with how proud the utilities were at that time to have distributed generation. In the days when they had started to power trolley companies. And this also would be a nice segue ultimately for Jeff, since he basically worked for a utility which was essentially its own microgrid for the town of Easton, and was able to power up the town when the rest of the state went blank in 2012 for that big straight line storm that we had. Okay, we're down to, we're under a minute. Okay, good. Well, what you'll see is an ad that we found in an old document, and the utility company was extremely proud of the fact that they had, in Washington County, Maryland alone, 23, I think it was, sources of power generation, including hydro on the Potomac River. They felt that that was telling their client base at the time, their customers, that their power was extremely safe because they had 20 some odd generating plants in a county alone. And if one or two went bad, no problem, we can keep the lights going. No one can make that claim today. And we're in Washington County, and I can attest to you that we do have frequent power blackouts. I only wish we had a few microgrids around like they did in 1956. So that being said, we're down to our last minute. There we go. Waiting for the results to pop up. If we have any results to pop up. Okay,
Yeah,
Brian.
Rick, it gives an extra 10, 15 seconds for folks to wrap up, but you should be able to see the results now.
All right. I see them. So 6 out of 53 thought that hydrogen would be the key. 6 out of 53 PV solar. 1 out of 53 for natural gas. 5 for nuclear power. All right. Was there, I guess I can scroll down. Oh, okay. Well, anyway, go ahead, Nana. We'll go to the next slide. That one slide I mentioned from 1956, if we could. And Brian, you'll be publishing all this as part of the final report too, right? I mean, the poll questions.
All of the questions will be saved. I can post them on the website if that's something that you want to do. Love to see a little more participation. There's a lot of folks that aren't accessing the polls, and if you need any help with that, you can contact me directly through the chat, and I can help you if you don't know how to do the polling.
Yeah, thank you, Brian. I appreciate that.
So Rick,
yeah,
we will be publishing a technical note that will include the results.
Excellent.
Of all the polls for all the sessions.
Okay. Alrighty, well, Nana, can you pull up that 1956 ad that was at the very tail end of our presentation?
Rick,
yes.
Yeah, this is already your last slide.
I lost it?
Yeah, this is your last page.
Oh.
So Nana, we can't see it. If you can share it.
I think she said that it was lost somehow. If that's the case,
it's the last slide, I think. Right.
Okay. There it is. Alrighty, serving the growing community since 1896 with cheap and ample electric power. Yes, indeed, the Hagerstown and Frederick Railway Company, the predecessor of the Potomac Edison Company, got that first plant going back then. But right now, let's see, they have they've grown. Now they have 21 sources of power now available to our customers in the area. And Ready Kilowatt, if you remember him, Ready Kilowatt is already planning for a big electrical future here. New generating units, new power lines, new facilities to help you live better. So thank you, Potomac Edison Company, 1956, and how important distributed generation was at that time. And we're kind of going back in some ways to that grand old model, not getting rid of the big plants, of course, but looking at these microgrids as being many small players in a very large network to add reliability and resiliency. And I just thought you guys should see this great ad from the 1950s that really heralded in distributed generation before it was called that. Okay, well, next up will be Steve Steffel. And as I mentioned to you before, he has had 10 years experience as being the manager of distributed energy resource planning and analytics. And Steve and I have known each other for a few years. I got to know him through a number of public events. He's always been on looking at the cutting edge of new technologies, and he's always been advising utilities to look to the future, not necessarily the 1956 future, but I'm eager to learn much more about Steve's own experience and his observations about the role of microgrids as we move forward in 2021. Okay, take it away, Steve.
Okay, well, thanks, Rick. And apologize, I'm not showing my picture. I got a number of laptops and computers in my desk, and they're off to the side. But we'll talk about some thoughts on microgrid from utility experience and several components that may accommodate the electric power paradigm of the future. First of all, the grid is kind of considered the largest man-made machine. And it is interesting, Rick mentioned the shift from centralized to back to distributed generation. I think the aspect of being able to produce components at a very competitive price is why we're starting to move back to distributed. I mean, had started a number of years ago with photovoltaics and other types of things, but certainly that is an interesting paradigm shift, and it does cause some challenges for the grid. But let's take a look at some thoughts on microgrids, starting kind of with the traditional. Then I'll throw out an interesting temporary microgrid concept that we looked at, campus style and public purpose. And we won't spend too much time on these, but just a little bit of an overview. We know that the traditional microgrid is put in a place generally where the business or the entities need some very reliable power, but also where there's heat and electric load that has a good profile to support the efficient use of generation and heat. Usually those two things have to be present to really make it efficient. And it certainly is something that would provide resiliency, as it can operate isolated, rejoin the grid, can provide ancillary services, grid support. Some of the microgrids make a fair amount of money with ancillary services and so on. But not every place is able to handle the traditional microgrid, and most microgrids didn't necessarily reduce emissions to zero. They did reduce emissions because they probably used the energy more efficiently, the heat and the power, but possibly this hydrogen efficient way of the future may really allow the microgrids to even be a lot cleaner. Now, we looked at an interesting thing of a temporary microgrid, and what I wanted to do was throw out just a little bit of a cost comparison. And so this is a second, and I have pictures of what we looked at. These are areas, but you don't need to focus on them. They dealt with the different critical components of a town, like, the hospital and fire and police and town centers and food and clinics and, pharmacies and gas stations and all the things that people need in a typical disaster, natural disaster. Well, this temporary microgrid that we took a look at, the second picture, was kind of an interesting experimental concept. It had two very, very large malls, 2 million square feet. It had hundreds of stores, services, clinics, grocery, gas stations, hardware, You know, basically almost everything the population in this southern part of a whole state needed. It was a little bit inland, so it wouldn't get blasted in hurricanes and so on. It had 12,000 parking spaces, so you could serve people with ice and water and food and distribution, and help them recharge their phones, provide communications. That was about an area that would be about 25 to 30 megawatts. And to do a traditional microgrid in that area, where it probably would have been around $100 million, it did have some solar already in it on a couple large buildings. But what we looked at was, what if we did a temporary type arrangement? So we looked at putting in all the switches, the control and communications to switch over to a microgrid. We put in step-up transformers to make quick connects to mobile generation, and you could do that for about $1 million. So I'm just showing a comparison. Now, eventually, maybe we'll be able to have mobile highly clean type of generation that could roll in, but if you don't have to put all of the microgrid components in, and you can roll them in as needed, you can have this type of temporary microgrid that can address emergencies or natural disasters. So kind of just an interesting concept in terms of the cost. And you could roll the generation in before a storm hit. You could roll it in very quickly after a storm hit, and you could have power for a whole area. Then there's the campus style microgrid, which probably is the most popular because it's the easiest to implement. You've got one entity, and hopefully they've got heat and electric profiles that make the microgrid efficient and help pay for that expense. And we do have a few campus style microgrids, mostly owned by outside firms. I mean, the utility was looking to see what could the utility do in a public purpose type of approach. And these are much more difficult, mainly to get all the parties on board. And, some people wanted, high reliability, some didn't care. Who pays what, who has the generation. It makes for a much more complicated a billing and arrangement type of scenario. But that's not the impossibility. It's just at this point in time, some of these things still cost a lot of money, and the utility has been PHI, where I was, has been improving reliability tremendously. And I don't think we serve you, Rick. It sounds like, but that's another component. If the reliability is high, people don't see the need, and of course the storms don't come too often. I mean, right after the storm, everybody might want a microgrid. After a couple of years, they, well, I don't know if it's necessary. So, anyways, I think microgrids, the cost efficiency is very important. The emissions aspect, very important, and all these components go into making something viable. Now, the next thing I was going to talk about, and we can go to the next slide quickly, and this is the three components that I think will accommodate the DERs of the future. And first one is smart generation. That's pretty much what you've been talking about. Figuring out how to reduce emissions and do it efficiently and have a economic type system. But I think some of these components are going to be really key to the future of the grid. You have thermal storage, and thermal storage is incentivized by proper tariffs, which kind of move to somewhat more of a real-time price for customers. So, they can use this thermal storage, so they're not using a lot of electric power during times when the heating or cooling would be more expensive. You got the battery energy storage, where utilities are doing it, private entities are doing it, especially where the grid is getting super saturated. But if the tariff is available, there can be multiple streams of income from battery energy storage as well as the thermal. V2G's probably still in its infancy, although we have at the University of Delaware quite a emphasis on doing this V2G. They've got vehicles all around the campus, and they do this and have promoted it quite a bit. And then you've got the hydrogen storage we've heard about. I see it as a promising thing. I know it's very difficult handling hydrogen, but you know, as those things are overcome, that'll be great. Smart inverter controls, there are some already in the system, and they're getting to be more widespread. There's local control where you can do volt var, and then there's centralized control. And I think for the larger inverter-based systems, there needs to be centralized control. One of the reasons is to maintain a reliable grid so that you can switch it, reconfigure it, isolate faults, and do those kind of things as necessary. So if we have everything out there locally controlled without a central control, it becomes very, very difficult to handle those kind of scenarios in the grid. So the next component would be the smart grid, and accommodating more renewables. Some of the things that are really necessary are voltage headroom on feeders and on the secondaries. There can be more dynamic voltage control where you've got smart controls that actually control voltage regulators and capacitor banks on the feeders so that you're getting feedback from smart meters at the customers. You're making sure nobody gets any low voltage or high voltage, and you can crank up voltages during high peak load periods and drop them down during high solar output periods, and actually accommodate what we call hosting capacity, increase the hosting capacity tremendously by controlling the grid in a much smarter way. But a lot of that still has to have some logic and development on the back end.
Right.
We've got another challenge is accommodating more EVs, and we're starting to see them proliferate. Residential, you know, have maybe the smaller chargers, but one of the big problem areas will be some super concentrated large customers like transportation, trucking, service entities, where they may have a lot of fast chargers. And so that location, which many times they're clustered in a city, that location will require a tremendous amount of extra power delivery, but it could also be accommodated by storage and maybe by a localized hydrogen-based fuel cell system or hybrid system. Interesting, in cities, there's secondary networks, and secondary networks have redundant transformation because you can have a transformer fail, and it takes quite a while to fix things in the underground network. So there typically is redundancy. And if you build in the smarts, you could put chargers off of that redundancy. And if a transformer failed, you just have that charger out of service, or that charging station location. So, I mean, there's some interesting possibilities there to take redundant distribution wire capacity and use it for future electric vehicle charging or other types of things. Smart grid, we kind of intimated already that we need better centralized control and distributed control. So some of the things need to be automated out in the system, but some of the things have to be, decision making has to be made in a centralized form. But a lot of that still has to be developed. There is advanced distribution management systems, but there's still a lot more logic and communications that's needed, a lot more interoperability, and then we need even improved cybersecurity because all of those new communications will require the protection from people trying to hack in. So grid edge generators, grid edge equipment will need a lot more communication and improved cybersecurity, especially the grid edge generators. Then we've got the smart premises and smart city, and this really deals with the load. There is already load control, but there probably needs to be a lot more flexible load control where the load can be controlled if it is not going to impact the lifestyle of customers. And that combined with some centralized control of generation, centralized distributed, will keep the grid reliable. I mean, one of the things that is making for a more reliable grid is the capability of the grid to isolate faults and transfer sections of feeders to other feeders that are viable. But with the presence of generation on the feeders, it becomes more difficult for those logic systems to determine where the fault is because you've got all these different things feeding the fault. And then to transfer those sections, all the generation went dead, and now it's going to come pop back up in about 5 minutes. So a system has to know, do I have to send a signal to turn off a couple of the generators? Is it during the daytime? Is it nighttime? What am I going to see after 5 minutes, after 10 minutes? So we're starting to work on building all that logic so that we can continue to adopt more and more DER, but reliability won't suffer. Then there's a lot of new sensors going in across the city. Both the utility and others are putting things in. Our utility's done a few pilots with, my past utility, with sensors for gunshot, traffic, parking, emissions, to help the city, smart city environment. Just had some presentations from folks at the University of Delaware. They're working with rapid photography that goes into a data base, and they can bind the data. They can do all kinds of emissions and cycle times and see the flow of people and lights and things turning on and off and different things. Very interesting. All the different things they can determine from that data, how to anonymize it and not have any specifics, but use it that way. So data mining is going to become really, really important in the future, helping to make smart city and even smart control of the grid thing of the future. So with that, I think turn it back over to you. And if there's any questions, we can either answer them now or later on.
Well, thank you so much, Steve. Sorry that we couldn't see that handsome face of yours, though. That's too bad. Anyway, the next speaker I'll get to in just a moment, dealing more with controls. But I would like to ask Brian if he could queue up the next or the fourth polling question, and I'll talk a little bit about it, about what's involved in the questions that are coming up. There we go. Great. Looking good so far. Anyway, the next question, when it rolls up, is going to be what factors or forces do you believe are the biggest obstacles facing widespread microgrid adoption? And the answers that we have as our predetermined answers or pre-selected: state regulation, such as the ability to cross a state road. I know when we were designing one of the first microgrids in the state of Connecticut, the state of Connecticut was the only state I knew of in the union that would allow a special exemption for wires from a microgrid to go across a state road. Otherwise, that that right, if you would, for exclusive passage of lines is something that's really a big inhibiting factor for widespread microgrid design. That may be changing now. I'm not sure if other states have altered their ways. I remember spending time with the utility, though, discussing all these elaborate switching mechanisms that may be required to allow power from a microgrid to replace the utility power during a blackout. I'm not sure, again, if all these things are necessary at this time and in what states, but that is a big issue. And then we have federal regulation, or FERC, lack of incentives and perceived cost. Of course, everyone knows that microgrids cost a great deal. Depends on which components that you add. Of course, a fuel cell is one of the more costly. Power industry resistance, interoperability with the bulk power grid, if that is problematic, and of course, just plain inadequate or aging infrastructure limitations. I know Steve and I have talked about how difficult it is to add renewables, I should say, add any new distributed generation on aging lines because the technology just doesn't exist to accommodate certain types of power. And I remember talking to the power company, Connecticut Light and Power, about the very great importance of any power back feeding off of the grid. We had to come up with a new design that involved some large diodes that would prevent power going back onto the lines. That's a common concern, but I'm just saying these are all issues that people have to address when they're designing a microgrid with a public utility. All righty, how are we looking here? Time limit, meeting time is 0. Okay, great. We do have our answers that kind of scattered almost evenly across the board. 3 people, state regulation, 3, 4, lack of incentives, power industry resistance, 3, interoperability issues, 2, and inadequate or aging infrastructure, 3. So pretty equally divided. I'm surprised. Absolutely nobody thought that FERC was a problem. So with that, I would like to move us all on to the next speaker, who will be Colonel Matt Baker, United States Marine Corps, retired. I have not had the chance to meet Matt. I learned about his company, though, because of our work at Tech Connect, and we were approached by members of his firm because I kept mentioning the magic words advanced power controls as being essential to what we're trying to accomplish. So I was very delighted to be approached by Typhoon Hill of Massachusetts. They have worked on some extraordinary modeling and for microgrid design. I know that according to their slide deck, Duke Energy is one of their largest clients, and I'm not going to waste any more time. I'm going to turn it directly over to Matt, and he can take it from there. The slideshow looks superb. Matt, please go ahead.
Hey, thank you very much, Rick. Can you hear me?
I can hear you beautifully.
Great.
Absolutely.
Nana, if you could go to the next slide, please. My name's Matt Baker. As Rick kindly pointed out, I was a Marine officer for 28 years. I retired in 2015. And when I got out, I cast about for a new career and ended up in hybrid energy. And we were taking basically diesel gen sets and hybridizing them with a little bit of lithium ion batteries and some PV, and making much more efficient power generation for military applications, microgrids. And we were always late. We were always over budget, and our stuff didn't work very well. And I went from being a business development guy into a project management guy to try to figure this out. And we hired this power electronics guy. And the first thing he said was, "Hey, we've got to have this thing called a hill." And I was delighted. I said, "Hey, I spent 28 years taking hills, but if you could just explain why that one's spelled with one L before we begin, I'd really appreciate it. And he explained hardware in the loop. And I went and asked all the other engineers. There were 8 of them. And to a man, they said, we don't need that thing. One guy said, hey, I can do everything that thing can do with an Excel spreadsheet. I direct quote. And but the power electronics guy was pretty persuasive. And we bought a Hill setup. And I knew we were successful because 2 months later, I walked into the rec room and there was a sign-up sheet with all the hours of the day. And I said, is this the donut sale to save the company? And everybody explained patiently, no, that is the sign-up sheet for the Hill. And I said, hey, Mr. Excel spreadsheet, I see your name all over this thing. And what's your explanation? He said, well, life is tough. It's tougher if you're stupid. So really what we're here to talk about is digitalization and control. I've got my own opinions, and the discussion by the previous 2 speakers and also the ones after deals primarily with energy sources. I'm a big fan of hydrogen like the next guy. But what we're really here to talk about is digitalization and the control of those microgrids as they either connect to the grid or disconnect from the grid. And if you remember your definition of a microgrid, it can be either islanded or connected to the grid. So there are 2 primary pieces here. And I'm going to pick up the pace a little bit so we can give back some time to other presenters. If you go to the next slide, please. When you're talking about microgrid control, you have to understand that microgrids are in anything that's digitally controlled that attaches to the grid and is doing DC to AC power conversion or DC to DC power conversion or AC to AC power conversion. If it's digitally controlled, it has to be incredibly fast. We see this word fast gets tossed around a whole lot. What do you mean by fast? Well, I've got a depiction here that if you look at the bottom of it, you see speed from nanoseconds to microseconds to milliseconds. And I've got 1 millisecond there as the far right. 1 millisecond of thousandths of a second. Most people in the electrical world think in terms of hertz, 60 hertz. That's only 60 per second. Very, very slow for what we're talking about. In order to control a microgrid, you have to have an incredibly fast controller. So incredible won't really cut it. What we say at Typhoon is you've got to have something in that pink column there, somewhere between 1 microsecond and 10 microseconds in order to make those rapid transitions that are critical to effectively having a microgrid. Whether it attaches to the grid or not, your controller for your inverter in particular is going to have to go that fast. That's from an operational standpoint. That is how the microgrid functions. It's going to have to be very, very fast. If you go to the next slide, the other aspect of digitalization is lines of code. So we've got these computers that are going to control all these different components of the microgrid, DERs, distribution. Your dumbest relay today is a full-on computer when you think about it. A Schweitzer 751 relay is a full-on computer, let alone the controls for your fuel cell and everything else. Every single one of those components has lines of code. And this depiction here kind of shows how lines of control are growing in the world, this digitalization of the world. You see the automobile. It was pretty impressive back in 2015. It's zooming forward. You can park your Tesla. It updates itself overnight. You walk in the next morning, turn it on, and it's got 5% improved battery performance. It's amazing. All of those lines of code and all of those different components have to be tested effectively. If you don't, you end up with this. Probably the best example is this Toyota example with the accelerator that nobody could figure out what the heck was going on, and it was an analysis of the lines of code. It was a digitalization problem. So if you go to the next slide, I was really pleased to hear this cyber physical reference with the hydrogen fuel cell development, because model-based engineering, which basically combines a model, the cyber piece, and the physical, some physical aspect of whatever you're trying to work on. That is the absolute focus of Typhoon Hill. But I think we turned it a little bit on its head, because our focus really is the controller. So in our mind, and you see on the left-hand side, the physical, the transmission lines, the inverters, everything like that, we think we can get very, very accurate models of those using our FPGA-based computing. And when I say accurate, I'm talking about that fidelity aspect. The reason why we have a specialized computing function is we have to be able to do deterministic calculations to see inside that microsecond. But we think we can simulate that fairly accurately. What we isolate or decouple from that is the actual controller. We want to put the actual controllers in the loop with the model that's actually the business end of those microgrids, the distributed energy resources. We want to model all those, and we want to put the controller in the loop with it in order to make what we call a C-Hill, or controller hardware in the loop test bed. Next slide. So with that controller hardware in the loop test bed, we can work on that integration, that compatibility piece that was referred to as it's really kind of the hard aspect of this. And in order to save some time, and I think really to make a better point with my presentation, because it's extremely related to everything that we're going to see today, and this is a great conference, and Rick Typhoon's very, very pleased to participate. Typhoon does have a very, very important role in developing those controls to make all this possible, as I'm sure you can appreciate. There's a whole lot of discussion on what the fuel mix is, what the sizing is, and everything else. What we're about is making those controls work effectively. So I sit actually in Norfolk, Virginia. My company is in Boston, but I get to watch Navy ships go by all the time. One of them is this brand new aircraft carrier, the Ford, that costs to the tune of about $13 billion. And apologies up front to my Navy friends, but I'm a Marine, so I get away with hassling the Navy. It's a freaking paperweight. And the reason is because they can't get all the power electronic components. It's really a microgrid at sea. They can't get them to play nicely because they have no way to effectively test all those lines of control over the life of the ship. So imagine in your microgrid, if you change out the batteries, or you change PV, or you add the hydrogen-based CHP plant. How do you do that? Is it a brownfield problem every time, or can you maintain a digital twin of it and simply switch out the controllers? That's what Typhoon's all about. So Nana, if you could flip ahead a few slides, I think I'll save the group some time. If you could go to slide 12, which is a picture of Duke Mount Holly, and everybody who's patiently listening, you'll have these slides so you can go through them. And you can email me, and we can have a further discussion if you like. But this is a Typhoon test bed at Duke's Mount Holly site right outside of Charlotte. And what they're doing here is grid modernization. And you see a list of all the Schweitzer distribution controls. Actually, each and every one of them a computer in its own right. They see reclosers, genset protection, transmission protection, et cetera, et cetera. together with cap bank, tap changer, and then there's that little Hitachi power store at the very bottom. That's the energy storage. That's the inverter that's being tested to see whether it can effectively island and then rejoin the grid. This is an example of a C-Hill test bed where you can really get after that control testing. And it's not just the individual components, you got to test it as a system. You can go to the next slide just to see another example. This one's particularly interesting. It's a commercial marine power system, but the reason why I think it's so interesting is ABB wanted to see whether an AC bus aboard the ship would work as well as a DC bus aboard the ship. So that's a whole other part of the microgrid discussion on whether or not we're going to go with Tesla, and his magnificent alternating current, or we're going to go with Edison and his equally magnificent DC current. But whether the two really didn't get along, we absolutely know their technology doesn't get along. So this is a test bed that goes after that. So Rick, I'm going to try to give back some time because I think that the focus of your panel here is on the actual microgrid components. But I thank you very much because I think control at the end of the day is the pesky little train wreck that if you don't address it, you're really going to have a problem. And hardware in the loop, controller hardware in the loop is the way to do that. Over.
Okay. Thank you, Matt, very, very much. And in the interest of time, and forego doing any more of those polling questions, so we can just go right on to Ronnie and his associates, Joe and Alexandra from, Centrica. And pardon me?
No, just at Centrica.
Yeah, Centrica, right? Anyway, Ronnie, I have known him for several years, great sense of humor, really understands the market for almost any kind of a client that needs a microgrid, whether it's industry, whether it's municipal, whether it's statewide. I'm just going to turn it right over to Ronnie so he can just run with it. Go ahead, Ronnie.
Well, Rick, thank you so much. It's an honor for my team to be here. Thank you, Dr. Tucker, for putting this together. Nana, thank you for all your work, putting our slides up and making sure they run properly. We really appreciate it. It's an honor for me to introduce the head of our optimization, Alex Coleman, is presenting, and also Joe. So Joe's in a really hard place to live. He's down in the Key West area, but Joe Walsh. He heads up all of our federal programs. So I'm turning it over to Alex, and thank you.
Sure thing. Thanks. I don't see the slides up at the moment.
Nana, can you put our slides up for us, please? Thank you.
Okay, great. And I think Joe, you're going to kick us off here, right?
Absolutely. I'm happy to. Thank you, Ronnie and Alex and Rick. It's great to be here. We are excited to talk. I think it's been indicative, the conversation we've had already, that what we're really talking about here is the nexus. Trying to solve this problem is the nexus of technical solutions, commercial solutions, and policy solutions. And so I have the opportunity to tell you a fun story here in just a second about a project that I think is a great example of those three things being able to come together. But before I do, I'm going to tell you just really briefly, in case you're not familiar with Centrica, you see the technical solutions listed across the top of the slide there. So Centrica is a 200-year-old company, would probably be most well known as the parent company of British Gas, so the largest energy supplier in the UK. And we have, as a company, have diversified in recent years to be able to tackle this challenge. If you'll take us to the next slide, please. I think what's most important about the perspective that our team is going to bring to this conversation is we are talking here about a global challenge. There's been conversation about utilities and the role that utilities have played historically in the development of our existing grid and what roles they maybe can play moving forward. I think it's really important that companies like Centrica that have 200 years of history of investment in the existing energy infrastructure that's out there are invested in finding ways of solving these problems. So as you see, the company started in the UK, as I mentioned. We also provide utility services in Ireland on the natural gas side, and then what would be sort of unregulated or non-tariff-based services globally. So as far into Asia as Japan and throughout North America. Now I'm going to take the opportunity to tell you about an exciting project in Northwest England, and then Alex is going to bring it back home to North America here, where most of us, according to the poll, are sitting. So if you could take it to the next slide. So this is a really cool project and something that's really exciting to talk about. So what you're seeing here is the Co2 battery system, about 50 megawatts of scale of battery energy storage, to give you some sense of the kind of size that we're talking about on this project. But what I think makes it really interesting is this site was the location of an old coal burning plant, later became the location of a combined cycle natural gas plant. And as the grid has evolved, and as the needs of the energy consumers throughout England and in Northwest England have evolved, this presented a really unique opportunity to take advantage of a location that is that's developable, that is located next to adjacent existing infrastructure, and be able to leverage all of that existing infrastructure to provide a really unique solution. So as you see on the slide, Co2 is about a 50 megawatt battery energy storage system. It has the ability to be responsive to the needs of the grid. So at a very basic level, it can absorb power from the grid or can supply power to the grid based on the needs of the broader electrical system throughout the UK. About 50 megawatts, or on the order of 50,000 homes for the scale of this project. So again, talking about evolving this system from a system 100 years ago that was burning coal, and being able to move forward and try to tackle some of the problems or the challenges that we've addressed in a few of the poll questions that have already been discussed. Now, this addresses technology. This addresses commerciability of a solution. Alex, I know you're going to talk about those things, but you're also going to talk a little bit about some of the policies that enable some of the exciting stuff we've done, like Co2, but in the U.S. and particularly in New York City, right?
Yep, sure. So if you can go to the next slide, please. So not only did we develop this project and operate it in the UK, but we also have a platform to control the project, right? So what Centrica does here is we have a controller, and we are able to access value from the market and have market access to do so, and then control the battery at that facility. We also control load, on-site distributed energy resources, in order to provide, as you can see in the middle here, we provide kind of megawatt flexibility to the grid. And in return, we then either, in the case of Co2, which Joe just described, pay back our investment via the revenue that we receive from the grid, or in the case of a customer with an on-site energy solution or perhaps load, what we'll do is we'll actually share that revenue with the customer. And so that's really what Centrica's virtual power plant is doing globally. Some of the statistics that Joe shared when we had the map of the world there, kind of showing what we do. We're really participating in markets such as capacity, short-term operating reserves, fast frequency regulation, and balancing mechanisms such as real-time energy market participation, in order to really balance the grid, in addition to monetizing these assets and ultimately buying down some of the costs that was identified as a big barrier for microgrid development. If you go to the next slide. So an interesting case study that we've done with the New York City Housing Authority, which we call NYCHA, is after Hurricane Sandy, NYCHA received federal funds to put generators on their facilities for resilience. And Centrica came up with a solution for NYCHA to not only bring those generators to site, get them developed, but to enroll them in the market to pay down the cost of that, but to actually pay for the O&M cost of those generators. And so the cost to operate those generators on site is nil, because what we do is we utilize the revenue that the generators get from the market to pay for the O&M contract for those generators. And so, you know, as the market has evolved in New York City, this is in Con Ed territory, of course. Con Ed had come up with the dynamic load management program, or what we call DLM. And this is really a day-ahead peak shaving program. And we were able, originally, the program was not meant to include assets like generators, but we had suggested and advocated to Con Edison to allow generators to participate because they're on the grid and they're able to provide the peak shaving that Con Edison requires. And so they do now allow generators, and NYCHA generators do participate in that program in addition to other programs. So I'll mention that, you know, I think as we think about commercialization and allowing these technologies, you know, this is an old technology being utilized in a new way, let's say, right, and participating in the market. But regardless, right, the mechanism that allowed us to really advocate on behalf of the project is the fact that Centrica shares the revenue with NYCHA, right? So Centrica, as the market expert, understands the opportunity for those market revenues to be accessed, wants access to those revenues, and therefore advocates on behalf of the projects that it works on to allow those revenues to be accessed to the project. That makes sense. So with that, you know, happy to answer any questions, and if not, yield our time back to the group. Oh, Rick, you might be on mute.
I didn't do that. I don't know. I'm sorry about that. Is that now? Can you guys hear me? Unmute.
Yep, we can, Rick.
Oh, no, now we can't. We could for a second, but.
Something keeps bumping me out, but that's okay. I just want to make sure, Dave and Nana, that we can run a little bit over. Is that okay?
Sure. We have a break after this. So yeah, go ahead. I mean, I think the discussion is interesting, so let's continue on.
Okay. Well, we'll continue on, and then you call the shot whether or not we can have the University of Genoa hop on too. That's entirely your doing. Okay. Jeff Oxnam is the Chief Executive Officer of American Microgrid Solutions, and I've known Jeff for some time. I believe, Jeff, you're also, if I'm not mistaken, the chair of the Maryland, not Energy Administration, but the Clean Energy Center. Is that correct? And now you're muted. Go ahead and turn.
Yeah, thanks, Rick. Yeah, I chair the Maryland Clean Energy Center as well, and have had the good fortune to work with the in that role with the Maryland Energy Innovation organization to help bring some new technology to the market. But in just a couple of minutes here, and I'll really truncate my comments. I'm going to talk a little bit about the market itself and where we see things going, and a side of the market that really kind of gets overlooked in a lot of these conversations. Go ahead, next slide, please. As Rick mentioned, I am the CEO and founder of American Microgrid Solutions. We provide turnkey development management services. What does that mean? We're the folks who are going out, working with customers, identifying the opportunity, and actually getting these systems built, deployed, and operated. Our role is essentially to take all of this great technology in these systems and get them out in the field. And Matt, Matt Baker, I would emphasize or re-emphasize your very key point there that we really see from a technology standpoint that the control system is the key to where everything needs to follow. The systems that we provide are hybrid power systems and microgrids. We're working all over the country, 22 different states. But what I really want to focus here is to take a look at where the microgrid market's going, and not just the large and complex projects we often talk about that are those marquee projects, but the much smaller but bulk of the market type projects that are hybrid systems behind the meter and small microgrids. Next slide, please. So based on some of the industry stats, we're looking at a $5 billion market today. This is globally on microgrids, growing up about 6 times by 2029. Huge growth anticipated. Systems are primarily owner financed, but energy as a service is really growing as a model to finance these. It used to be that the market was dominated by remote microgrid systems off grid, but now these grid-tied systems are really catching up and becoming a key part of the market. One area that I'll jump right into, where we spend a lot of time and focused on, is in the mid-market or behind the meter systems. You know, when we think about the U.S. building stock, the median size building in the United States is only 5,000 square feet. Buildings that are considered large, 100,000 square feet or more, make up less than 2% of the stock. So a lot of the commercial real estate footprint that really is going to benefit from hybrid power systems and microgrids is not necessarily the focus. We see a lot of the larger campus style microgrids, a lot of the big building focus, but tremendous opportunity out across the market. What does that market want when they look at these systems? When we work with customers, they're really saying, hey, we're looking for 3 key things: savings, security, and sustainability. I think it's a mistake to think of microgrids as really just being about resilience or backup power. We're going to, turn them on only when there's a power outage. In the United States, you can expect reliability somewhere on the average of 99.999% of the time. So the resilience is only a small piece of the driver puzzle, absolutely critical when it gets there. It's the rest of the time that we really need that microgrid or hybrid power system to be delivering value. And as Alexandra just pointed out, in New York and in markets all over the country, they really are on a day in and day out basis. So our emphasis in American Microgrid is trying to design systems that bring that value, bring that value stack day in and day out to our clients. Next slide, please. So looking at the market, where things are going, there's a lot of tailwinds right now helping things along. We're starting to see rising energy costs after a period of flatline. When you look at sort of the average of a lot of markets across the country, we're expecting to start to see a gradual climb up. We've seen a lot of high-profile grid outages that are really driving interest from the resilience standpoint. And at the same time, we're seeing falling component costs that are making these solutions a lot more effective. Again, as Matt pointed out, the control technology is absolutely critical to the success of what's happening. And to us, that's a real breakthrough, as is Rick's point about hybrid solutions. We're big fans of hybrid systems that create flexibility and versatility so that you can tailor a solution to the market it's being deployed in and maximize the value for the customers. The financial side of it, sometimes the financial engineering is as important as the electrical engineering, and the innovations there have helped. Of course, the big push towards renewable targets and incentives at the state level is a big driver. But we're still facing headwinds, and this was one of the questions polling earlier. There's this regulatory disconnect. The regulations are designed to support a system architecture that is over 100 years old and have not caught up in individual markets really to be able to embrace a distributed or hybrid systems. Resilience isn't priced in a lot of places, and that is a big disconnect. Resilience is, to some people, what it matters when the lights have gone out and they're without it, but not in advance. They haven't been able to figure out for themselves what that cost is. In some markets, it is patently obvious. Data centers can get you down to the nanosecond, but not for the bulk of the market. We spend a lot of time working with customers to help understand what the cost of resilience is. Incentives aren't fully mature. We are seeing some great progress being made across the country, and they're coming along, but it's still not there. Unfortunately, a lot of projects still have marginal returns, though, again, in certain markets, we're seeing a lot of projects that go ahead and pencil and are bankable. I'll mention two things and jump out of this. The competition for control of microgrids continues to be a headwind creating drag. Who gets to control the business model? Who gets to make sure that the assets are generating return for whom? It's a complex question, and believe me, as a recovering utility executive, I appreciate how hard and the various audiences that have to be served, but there is a lot of friction there. Finally, the pilot project mentality can be detrimental, I think, to deploying a lot of projects. We still too often fall to looking at microgrids in applications where they're ready for prime time as being pilot projects rather than hitting the market with tools that need to be deployed, even if they're phased in over time on a scalable way. So, and if you could just go to the last slide, we'll save some time here for our last two guests. I want to thank everybody for your time, and Rick, thanks for having me. And at American Microgrid Solutions, we're excited to take all of this great technology and get it into the field for you.
Thank you very much, Jeff. Very, very much. Dave, I'm going to toss the ball back to you and to Nana. It's exactly 11:30. But if you can extend the time to allow the two students to present and have any other dialogue, or it's entirely up to you. You call the shot.
Sure. No. So yeah, let's go ahead. We'll just try to keep it short, but we'll go ahead and cut into the break a little bit so that they can talk. Because we love students. We like to see what they're going on, and we know that they have a really awesome experimental microgrid at the University of Genoa. So
tremendous. Okay.
Who's on the list to talk next?
Martina.
All right, Martina.
Hi. Good morning or good afternoon, everyone, and thank you for letting me present my presentation. Anana, do you have the slide, or do I have to share?
Yes, I can share for you if you want me to.
It's the same. Otherwise, I can share it.
So, Martina, why don't you just go ahead and share your slides? That way you can control when you go through them. And remember, we're kind of on a time constraint here, so.
Yes, I will. It's gonna be very quick.
No problem.
Sorry, I'm having some troubles with the...
I have it open if you want me to.
Okay, that would be better because I'm having some troubles. Okay. Yes, I am Martina Raggio. I am a PhD student at the University of Genova, and my main research field is about energy storage systems and integration with the micro gas turbines. And I would like to give a very short summary about small-scale compressor energy storage systems and some challenges with the integration. So can you go with the next slide, please? At the University of Genova, I'm involved in a project that is called Next MGT. It's a European project that has the main aim to improve understanding in general of micro gas turbine, and it's including different universities. Every student involved is studying a different topic, and as I said, I am studying integration with energy storage systems. As already also said in the other presentation, there is a focus in renewable energy sources because of reduction of CO2 emission and in general of pollution. Also, there is an interest in distributed energy sources in order to maximize power production and also integrate even further the renewable energy sources. There's also then a need to use energy storage system, especially in microgrids, to basically balance the demand and supply. And then there are also many different energy storage systems with different applications. In this case, I would like to just focus on compressed energy storage system for a small scale application because they have some interesting features. For example, they don't have any particular charge or discharge problems with degradations. They also don't need any particular protection for working at high temperatures. Also, they are suitable for cogeneration, trigeneration, because during a compressor, you heat up the air, so you can utilize the heat. Or also during the expansion of the compressed air, you can cool down the air and utilize it for cooling purposes. Also, for a small application, it's possible to use some vessels, for example. So there are also no very specific geological constraints. Can you go to the next slide? So I provided a very quick review, not complete, but with the main strategies of compressed energy storage. In general, the principle of a conventional system is the following. So during peak periods, for example, with a high availability of renewables, we can run a compressor and store the energy in a storage system. And then when we need energy, we can first heat it up in a combustion chamber, and then produce electricity by expanding in a turbine. There is, let's say, a disadvantage is that we still need to use some fuel to heat up the air. So there are other options, for example, adiabatic solutions, where we also use thermal energy storage systems. So in this case, let's say, we can store the heat during the compression and then utilize it later before the expansion. Or there are also other solutions with isothermal compressor, so trying to have a near isothermal compression or expansion. But it has to be noted that the second and third option are very difficult to be implemented because they require a lot of cost and research. So I would like to propose another overview, another strategies, second generation compressed energy storage, and this one consists of a micro gas turbine and so a commercially available micro gas turbine together with another compressor and storage. In this case, we can use already an available micro gas turbine and decrease cost, and also improve flexibility of the plant. So can you go to the next slide? And in this next and last slide, I just would like to highlight some of the challenges with the integration with micro gas turbine. This is presented study with the T100 micro gas turbine. It's a micro gas turbine with a nominal power of 100 kilowatt. So for this kind of application, we are using the micro gas turbine with the augmented gas mass flow, because we are injecting during the discharge phase, we are injecting air. So there are possible problem with the compressor instabilities that can lead to compressor surge. So it's important to study this phenomenon and understand what is the maximum achievable mass flow, and this has been done with the transient tool. So I just show here some results. This is the surge margin. So it's just an indicator that has to be above roughly 1.1 according to the definition proposed here. And this simulation allow me to understand what is the maximum mass flow that can be injected. And in general, it can be noted that at higher mass flow, at higher power setting, higher mass flow rate can be injected. So I think that this is the last slide. So I would like to thank you for the attention.
Thank you, Martina. It's very lovely to meet you. We all appreciate it very, very much. And Dave, I don't know if you have a second speaker.
Is there some?
There have
no. Okay, I guess there is.
Okay, Dave, take it away.
Avinash, okay.
Hi everyone. It's good to see a lot of familiar faces here. So thank you, David. Thank you, Rick, for giving me opportunity to present today. I'm Avinash from. Can you hear me?
Oh, wonderfully! I just acknowledged and thank you very much.
Okay, thank you. So, so this is Avinash Renuke from University of Genova. I'm also a PhD student, and I will be introducing you a couple of topics. One is long-lasting batteries, which is one Horizon 2020 European project. And another topic, which is energy harvesting technologies to improve cycle efficiency. Next slide, please. Thank you. So as we know that the battery storage systems are the key enabling technologies to integrate renewable energy sources into electric grid. So it is important to improve the battery cell performance, cell safety, and the sustainability. So this is the objective of this European project, which is called LOLABAT, long-lasting battery, and the focus is on the nickel-zinc battery system. And the application is targeted for the stationary energy storage. So you can see the comparative chart below, which shows the comparison between lithium-ion batteries, lead-acid battery, and the nickel-zinc battery, which is realized in this project. So what are the key features? Like one is the cell performance improvement. So you can see the energy density of the nickel-zinc battery is improved, will be improved compared to the lead-acid battery. Okay, and also the number of cycles with per 100% depth of discharge will be increased from 2,000 to 4,000 at the end of the project. So these are the two important key points. And the third point, if we compare with lithium-ion battery, which is most widely used battery system, the important issue is here is the safety, okay, and the sustainability. So nickel-zinc battery, as the raw material is widely available and it is non-toxic, and the material is it has high recycle potential. So compared to the lithium ion, it is the best battery for the large size to be used in stationary energy storage systems. Next slide, please. So you can see here there are 17 European partners. So we are University of Genova, one of the partner in this project, and the lead coordinator is Sun Energy based in France. Next slide, please. So here you can see the KPIs of this project. So as I said earlier, the cyclability, which is number of cycles from 0 month to end of the project, we have 100% increase. So 4,000 number of cycles, and the cell cost to be reduced by 30%. Next slide, please. And these are the demonstrations, several demonstrators for this project. For example, energy balancing in the smart buildings is one. Then we have hybridization of hydraulic power plants. Then we have industrial application, and the two main applications regarding smart distribution grids in the Savona campus in UNIJ, and energy storage for a remote application. So these two demonstrations will be done at UNIJ. Next slide, please. Now let me come to second topic, which is the energy harvesting expander, which is non-conventional expander. It's called Tesla Bladeless expander. So you can see on the right-hand side image where it consists of only flat disc, mounted on the shaft with spacers between them. So the idea is it doesn't work on the impact force, it works on the principle of boundary layer. So you get the power using the viscous shear between the fluid and the disc. So viscous friction is actually in the favor of production of power. So this technology is like century-old technology, patented by Nikola Tesla, early 19th century. Now it is gaining a lot of interest in the very niche applications like heat pump, energy harvesting in heat pumps or chillers, or organic racking cycles in waste heat recovery applications. So why it is interesting? First of all, it's low cost, low maintenance. You can use any fluid here. It is reversible machine. So if you see the rotor, there are no blades. So if you just reverse the direction of the rotor, it works as a compressor. Okay. There are no negative scale effects. If you scale down the machine, like in conventional machine, you have a viscous friction problem, so the efficiency goes down. In this case, we don't have that problem. Now, why it is not so popular? Because of course the performance, the experimental performance has been seen very low, recorded very low. So in the University of Genova, we are extensively working on these machines with a different variety of fluids. Next slide. Let me introduce you to some applications in two-phase machines which we have built and actually integrated into the heat pumps, actual heat pump systems. Currently, it is under testing. So you can see this is a butane expander, two-phase bladeless expander, which we have developed at UNIJ, and it is currently under testing. So you can see on the right-hand side pH diagram where we are expanding from subcooling to the two-phase region. And the machine is highlighted here in this yellow circle, blue circle. So we are expecting some power out of it. Expected power is 300 watt for this. Next slide, please. And these are some machines which we have built. So you can see we have built for several different refrigerants or the fluids. For example, air. We have the prototype mainly for the research purpose. Which is designed for 3 kilowatt system at 30,000 RPM. Then we have R134A refrigerant, which gives isentropic power of 1 kilowatt. Then we have water, which is a simulated case for butane liquid case in heat pump, where we have a 2 kilowatt isentropic power. And then we have another machine which two-phase butane again, which is another part of European project. So all these machines are developed. Now they are under testing. So we have pretty much extensive research and experimental testing going on in our lab. So next slide, please. So if you are interested in any of these topics, the long-lasting batteries or Tesla expanders, please don't hesitate to ask me. You can write me an email, or you can ask me in the chat window any questions. Thank you very much.
Thank you very much.
Yeah.
All right, Dr. Chen.
Okay. Is that it, Rick?
Unless you have somebody else, I can see that we're really running out of time now. So there will be no Q&A discussions. But Q&A, but covered an enormous range of good topics. Very strong. Thank you, Dave.
Yeah. No, thank you, Rick, for organizing the session. I think that there are definitely a lot of really good points, and certainly have lots of questions. But I think go ahead and communicate through the chat. I guess we'll take a 10-minute break. So Brian, I don't think we will need the breakout rooms. We just don't really have a lot of time. We'll give everybody 10 minutes to kind of stretch, and then we'll start with something completely different. We'll start in on the technical aspects. So, in terms of hybrid power systems, and that session will be chaired by Professor Alberto Traverso from the University of Genoa. So thanks again to all the speakers. You guys did an amazing job. I feel like I know a lot more about microgrids, enough to be dangerous. So
we'll get you there.
Yeah.
Wonderful. Well, I'll talk to you very soon, Dave. Sure. Talk to you very shortly, I hope, Dave.
Okay. All right. Yep. Thanks, guys.
Okay.
We'll be back in a few minutes.
All righty. Thank you.
In our next session, which is on cycles, hybrid power cycles, and the chair of this session will be Professor Alberto Traverso from the University of Genoa, who has been involved in hybrid cycles since before I can remember. So for a long time. I think even his dissertation was based on coming up with modeling tools to look at different cycles, if I'm not mistaken.
Correct.
Correct. All right.
Thank you.
But before I let you hit the road, Nana is going to make go through the mandatory slides that we need to show at the beginning of every session to make sure everybody's on board.
Yes, and this is to let everyone know that this meeting is considered as an open to public meeting, which means all the information in your presentation and in your discussion should be publicly available before this meeting. If you have sent me your slide ahead of time, it is public available because we have posted it in our conference page already. If you have published the data in some papers or report, then you are good to go as well. So just don't, include any sensitive information or those information has not been published or reported before. Another thing is that the entire workshop will be recorded to develop a technical note after the workshop, which will be available to all the participants, and we will send it when it's available. And also, we suggest that you to turn on your camera when you are talking, which I don't know whether I did. I hope it's not too late to turn on my camera, even though I give you the suggestion. Because we have many audience online at the same time, and we suggest you to mute yourself, except when you are presenting or you're asking questions and answering the questions. We encourage you to interact with the presenters. You can post your questions in chat while they are presenting, or you can join the discussion after the presentation. I think that would be it. So Alberto, you can take it away from here.
Thank you, Nana. Thank you, Dave, for your kind introduction and organization of this LEAP 2021. I would like to remember when we worked together in Morgantown in 2010, and we had this crazy idea of starting these workshops. We didn't know at the time which name to give to these workshops. We thought to Mr. Armstrong on the moon, who made a big leap for the humankind. So this is where the real name is coming from. Okay, so this session is actually about integrated and hybrid energy systems, where we want to discuss any potential and promising mixing of technologies towards a clean future. In this session, we are not talking only about integrated energy systems, we are also talking about integrated population systems, because in this session, Italy is calling, United States is answering, also Sweden is answering, Germany is answering, Japan through Germany is answering, and many other countries for sure. I'm just citing those involved as speakers, as panelists, which I'd like to thank for their availability. So all these people actually are integrated by a love in energy, and we share passion in power. So we want to be powerful, not necessarily clean, but of course I'm joking a little bit. So this will be a powerful session, integrated powerful session. So I will not spend more words, because 3 speakers out of 6 will be from my team. So they will speak on my behalf of what we are doing here at the University of Genoa. And so let me just go through the titles of the presentations. We're going to have 2 presentations about the thermal energy storage integrated into power plants. So the role of energy storage into combined cycles in that case. Also, we're going to have another presentation by Mccarrini about carbon dioxide, potentially supercritical carbon dioxide cycles for energy storage. So a very different application, very different point of view. We're going to see also something about marine applications of hydrogen and fuel cells from a researcher perspective, but by Matteo Cavo, but also including the industry perspective on that. Then we're going to receive a speech about an innovative combined heat and power cycle from Coma Science. And then also we are going to hear for the first time, in terms of hybridization, a nuclear hybrid system from Dr. Boardman. Finally, we're going to close with Dr. Agranotis from Mitsubishi Power Europe about their portfolio for the decarbonization of the future and encompassing SOC hybrid, pressurized hybrid. And finally, Dr. David Tucker will close with the novel concept of integrated system. So let me give floor for the first speech to Mr. Dr. Tommaso Reboli. Dr. Tommaso Reboli is from our lab. He's going to talk about the integration of thermal energy storage into combined cycles. And he received a PhD from University of Genoa last year, and is currently working as a postdoc onto a combined cycle, heat pump, thermal energy storage integrated system, run also as a cyber physical system. That's why he will also presenting in the last 2 days of this workshop. Tommaso, the floor is yours.
Thank you, Alberto, and good morning, everybody. And thanks to invite me to this workshop. And I'm going to share my screen. Okay. Can you see my screen?
Yes.
Okay. Also in full mode, I guess. Okay. Good morning, everybody. And my name is Tommaso Reboli from University of Genova. And today I'm going to show you some experimental results on our cold thermal energy storage of 180 kilowatt hour. First of all, a brief introduction. I am a research fellow and postdoc, as Alberto already said. I'm part of Thermochemical Power Group, that is a research group of University of Genova that involved more than 25 people. I will spend some words about the Pump-It project, that is the Horizon 2020 project, within which our cold thermal energy storage has been designed and developed and also implemented. The aim is to increase the flexibility and the operative range of the combined cycle through the integration of heat pump and thermal energy storage. We got 2 different layouts. The first one is the combined heat and power configuration that includes this warm thermal energy storage, while the power-oriented configuration includes this cold thermal energy storage. And to validate this concept, we built an experimental facility where these components are physical, while the bottom cycle is virtual and the behavior is evaluated through a dynamic real-time model. This is a picture of our experimental facility, where the main components are underlined. And for what concerns the cold thermal energy storage, this is mainly based on is mainly a shell tube heat exchanger, where the heat transfer fluid, that is a water glycol mixture, flow through the pipes, while the phase change material is on the shell side and is connected to this external compensator. We monitoring the temperature of the phase change material at different level and different depth, and also the pressure of the phase change itself, because this is closed circuit. Just to underline that at the beginning, this thermal energy storage has to be filled with paraffinic-based phase change material, and the requirement was 100 kilowatt-hour of energy. But actually, we filled it with the water, and we are evaluating the performance with the water as phase change material, and we strongly overcome this requirement, reaching more or less 180 kilowatt-hour of energy storage. We operate this component in two modes, what we call the charge mode, that is when we fill the test with cold power, and in this charge mode, with which we deliver the cold energy to thermal load. This is an additional picture of our plant. Here in this, we are now characterizing this equipment in charge mode. This is a plot that is quite interesting, because underlying the behavior of the phase change material, that is in this case is water, and here you can see the trend of the temperature at different layer of the water during the charge phase, and we can identify this discontinuities here. And here the phase change material also reach temperature below 0 degrees Celsius, and this is quite well-known phenomena. That is the first one is this is the density inversion temperature, while in this case we got that subcooled water, and in this part we got an instant icing process. That is quite similar to this shown in this video. This affects also the performance of the component, as you can see here. This is the power shared by the thermal energy storage, where we have this step in correspondence of this instant icing process, while this is the energy curve that, as already said, overcome 180 kilowatt per hour. So we also link this the power and the energy to the pressure of the thermal energy storage, in order to have some information about the state of charge of the thermal energy storage by knowing the pressure. And we are performing also some comparison by changing the mass flow and by keeping the same inlet temperature, or by keeping the same mass flow but changing the inlet temperature, or with the same inlet temperature and same mass flow, but with different direction of the heat transfer fluid. And in addition of this, we are also performing some evaluation on the dynamics response of this equipment. Here there are some step response. The way with which we regulate the power of the thermal energy storage in discharge mode is by varying the mass flow that pass through the equipment. And here you can see that this system is a second order system with this very huge overshoot here that make this component not very easy to be regulates. That's why we approach this problem with two ways. The first one, let me say, more empirical one, and the second one for the second one, we built a transfer function in order to model this component and to evaluate the dynamic behavior of the thermal energy storage. And with both approaches, we had some indication of the PID parameters. In particular, we find that in this case, for this equipment, we should impose a negative value for the derivative time. Just some conclusion discussion. This is a called thermal energy storage. It is a static equipment that can be very useful to be integrated with industrial energy processes, also civil maybe. I've shown you some ongoing activities on the characterization in charge mode and also on the dynamic response. For what concerns we are approaching in next future the discharge characterization of the thermal energy storage, and we will do it for our purpose, for our plant requirements, but maybe there should be some specific industrial application to be tested and to let this test discharge characterization more suitable for. And for what concerns the control strategy for dynamic control of the power, maybe there should a smarter approach than the one we are using now. We are now controlling the mass flow of the heat transfer fluid that circulates through the components by PID control, as already said. Maybe there should be a smarter approach that also can consider the state of charge and load characteristics. We got some idea on it. We are still working on it, but maybe obviously we are open to some suggestions. And with this slide, I end my presentation. I would like to thank you so much for your kind attention. Obviously, if there are some questions or curiosity, I'm available.
Thank you, Tommaso. We will collect all of the questions at the end for the plenary discussion. But let me ask anyway a quick question for you. So yes. You have been working on a thermal energy storage called thermal energy storage. And so you have been mentioning the synergy with the gas turbine. So my question is, in your experience, because you built it and you are working on it with the micro turbine as well, is a thermal energy storage, or can a thermal energy storage be operated in an equivalent manner than an electrical storage like a battery, or not?
Depends, because I think it's quite different the way, because in this case we store energy in form of cold energy, as you said. But for do that, we have we are forced to use also an additional component that is the heat pump, with which we can absorb and can regulate the net power.
Plus a heat pump and thermal energy storage, they can be probably a battery.
Yes, can be equivalent. Also because this storage we are storing cold power, and obviously to do that we absorb power from our cycle, and we can also reach power level below the minimum environmental load. But also we can recover this cold energy by conditioning the inlet of the compressor micro gas turbine here, with which we can increase the power of the cycle itself, so recovering the energy previously stored.
Thank you, Tommaso. Very interesting. We'll be talking also at the end. Thank you.
For sure. Thank you.
So let's give the floor to next speaker, who is Dr. Justin Chu. Justin, you can meanwhile prepare your presentation. And so Justin is working at the KTH, the Royal Institute of Technology in Sweden, where he is specializing in thermal energy storage. He's an active member of the International Energy Agency platform for energy conservation through energy storage. So he has a, say, international overview. He's currently the local director, I suspect in Sweden, for Erasmus Mundus double degree master program in the centralized smart energy system. So Justin, the floor is yours.
It's my pleasure to be here at your session. and also presenting for the first time in this workshop. So the title of my presentation, it is in line with Tommaso's presentation, but in higher temperature, slightly higher temperature. So storage in heat pump and heat management systems is the title. We will start with some motivation over here. So as we know, the load very often differs from the supply of energy because of intermittencies and peaks and off peaks. And then we see that often when we have peak load, we have a higher electricity price. So one of the goals here that I'm presenting at today's presentation is to overcome this, or let's say that we are, one of the goals is to achieve peak shaving and load shifting. As Tommaso previously presented, it is possible to integrate a cold storage to a power cycle, but then it's also possible to integrate a warm storage at the outlets of the waste heat recovery. And then if we combine it with a heat pump, for instance, we can store heat either on the condenser side, or we can store heat as a heat source on the evaporator side, depending on how we operate our heat pump systems. And of course, at the end, the goal, the end use is to provide heat to the users. And in this specific case we're presenting here, we're looking into using thermal energy, latent heat thermal energy storage with phase change materials. So, well, today I'm going to present some of the work we have performed also within the Horizon 2020 project, Pump Heats, where we looked at different types of phase change materials, different types of component design and system integration. Finally, some of the results on the economic feasibility will be presented. Here are some of the phase change materials that we used. So there are materials phase changing at 58 degrees Celsius. So here we're talking about Celsius and 60 degrees Celsius. And then here, from these pictures, you see some of the components that we have established and built at our lab. So either we fill in our phase change materials in cylinders like this, micro encapsulations, or we use different ellipsoidal form of encapsulations to enhance the heat transfer rates. So when we integrate a thermal energy storage to a heat pump, for instance, so that we can shift the electricity load from peak time to off-peak time, we do experience some coefficient of performance drop on the heat pump system. And here in our work, we are comparing, benchmarking, and proposing different types of solutions where we integrate our thermal energy storage, either us over here on the superheater side of the heat pump, or we can add a booster heat pump cycle, so an additional vapor compression cycle, or we have a combination of these two. So here we see this is the condenser side of the heat pump, where we extract the heat and to store it in our thermal energy storage system. Some preliminary conclusions, which have led to the graduation of one of my PhD candidates, Dr. Tian Hao, who is now in Tsinghua University in Beijing. We analyzed the different types of scenarios with use of ammonia heat pump in a 3-story multifamily building in Stockholm. And then instead of instantaneous coefficient of performance COP, here we are benchmarking with the weekly performance factor, where we have the total thermal energy divided by the total input electricity power. And we see that with the optimal design, we can reach 22 to 26% higher weekly performance factor, so higher COP over there. And then from the environmental perspective, where we study the CO2 emissions, we can reduce the CO2 emission by roughly 30%, so 1/3, as compared to the system without any thermal energy storage. One of the reasons is that with thermal energy storage, we can operate our system more efficiently during off-peak hours where marginal electricity production is not needed. And then from the economic perspective analysis, we see that the operating expenditure will be lower when we have our latent heat thermal energy storage, due to the fact that we're operating it off the peak hours. And then this would justify the slight increase in our capital expenditure with integration of storage. So here we do have potentials with such an integration of thermal energy storage. There are, of course, some additional future outlook, additional work that we can delve into. So the search for thermal energy storage materials, so latent heat thermal energy storage materials, will continue. We are looking for high storage density material. We are looking for small temperature swing material, and also materials with suitable phase change temperature range. Some of the bottlenecks or challenges we're facing right now are the low thermal conductivity, the phase separation that Tommaso earlier also presented for the other cases. And then I would say one of the most eminent bottleneck is that there are not enough experimental validations. And this is something that we are all among the research communities are working on. And I believe we will have a number of validations in the near future that would promote the rollout to the market of such integration. With this, I would like to thank you for your attention. And I would like to hand back the floor to Professor Traverso. The floor is yours. Thank you.
Justin, thank you for a very nice presentation. Actually, we are talking about a similar topic of Tommaso, so still about thermal energy storage, but a bit higher temperatures, which probably the application is more like microgrids for cogenerative applications or district heating. So my question for you, quick question is, what could you comment of latent versus sensible heat storage?
Thank you for the question. It has been a very, how do you say, a common question that comes up quite often. So I would say sensible heat storage systems are more mature, technically speaking. And one drawback I would say is that sensible heat storage, they take too much space. The temperature swing is larger. So with a phase change, we can limit the phase change temperature. So our working temperature can be maintained at a more like constant level, while the sensible heat storage, you would experience a large temperature drop or increase depending on if you're charging or discharging. So those are the two main, I would say, differences between sensible heat storage and latent heat. And now also, since we're looking for like more compact systems, smaller in size, especially for if we're talking about mobile thermal energy storage systems that we wish to transport, or we wish to have it on board of vehicles, then the size and the volume, the weight, they are all very important.
Thank you, Justin. Very nice question. Very nice answer. I understand you must be talking in favor of the phase change material, of course.
Not always. It depends on the application. So if I expand a little bit on the answer, so we know that in buildings, sensible heat storage, so water storage, they do have other purpose, such as for putting out fire. So that is some advantage that we can get with sensible heat storage. So multi-purpose.
Yeah.
So it depends on the application, definitely.
Thank you. And so I think we can move to the next presenter. I would like to, let's say, advise that please write your questions in the chat. we will collect it and then ask all together to the speakers at the end. So I'm just making some quick questions for clarification to the single speakers at the moment. So the next speaker is Simona Mccarrini. Simona Mccarrini is a PhD student in my team, and he has background on supercritical CO2 cycles, and he is actually part of the team who is going to follow the STEP project in the United States with the first megawatt size demonstrator in Europe that will be built by Nuovo Pignone and Tosi Meccanica as two machinery manufacturers. Nuovo Pignone is actually Becanayux for the compressor in Spain in some years. But he's going to talk about a different application of supercritical CO2 cycles. Simone, the floor is yours.
Thank you, Alberto, and thank you, everyone. And good morning or good afternoon to all of you. So I'm Simona Mccarrini, PhD student at the University of Genova, and I want to talk to you about the application of carbon dioxide for energy storage. So just to have a quick presentation about two systems, basically, because we need energy storage in the grid mainly because the unpredictability and non-dispatchability of the renewable energy sources. So this is in general, and can CO2 help in this way? There are many studies on supercritical CO2 power cycles because of a high efficiency and very high density. So let me say small turbo machinery, and hopefully also a smaller cost of the components. But in these two applications, there are slightly different application of carbon dioxide. These two are the CO2 battery, which is a system similar to the adiabatic CAES, so compressor air energy storage. And another one is the Carnot battery, or pumped thermal energy storage, with the application applied with supercritical CO2 cycles. So basically, first of all, I want to talk about the CO2 battery. This is a concept made by the Italian Energy Dome, and basically it can, it serves to store both pressure energy and thermal energy. So to do this, we have a similar application to the compressor air energy storage, but with the CO2 evolving. So we stay with CO2 in a supercritical phase, but we go anyway quite high in pressure, so around maybe 60 bar and so on. And so there are basically two storages, one a dome at low pressure, and then the CO2 is compressed up to a liquid phase. Here it can be stored at a high pressure and low volume, maintaining a temperature basically near the ambient temperature. And then in a discharge phase, we can reheat this CO2 with the use of the thermal energy storage we previously charged, and then expand in a CO2 turbine, not supercritical in this case, and so return to the starting point where we have CO2 basically at ambient pressure and temperatures. So, which are the advantages of this system? Of course, there is no need for a specific geographical location. And also it has a higher round-trip efficiency compared to pumped hydro storages and CAES. Also, as reported in this paper, also a lower levelized cost of storage compared to lithium-ion batteries can be achieved. Basically, if you want to see on the temperature entropy diagram, the system works in this way. So there is starting from basically ambient temperature, there's a compression, charging of the thermal energy storage, and then storage in a liquid phase, high pressure and liquid phase, and then the discharge phase in reverse, let me say. While the second system I want to present you is the so-called Carnot battery with an application to this time supercritical CO2 cycles. So this is made basically to increase the efficiency, the round trip efficiency of the systems, and in general, the Carnot batteries are composed by a charge and discharge phase, basically a heat pump cycle and a power cycle following, and they can be very, high scale storages can be achieved in this way, at least theoretically, and also this time there is no geographic constraint, so this is a huge advantage for this technology. Moreover, this system can possibly be integrated with the CSP or waste heat recovery system. So in this way, letting the charge phase or the discharge phase combined with the different systems, so having different temperatures between the charging phase or the discharge phase. And so, in specific for supercritical CO2 application, we can see, as reported from this paper, which is that quite high round trip efficiency can be achieved operating with supercritical CO2 cycles, going quite high in temperature, but always in the limit of the main molten salt application temperatures. So this is a quite high round trip efficiency, especially if compared with the same system, so Carnot batteries in general, but applied to ideal gas cycle, with a Brighton cycle, of course. A more ideal approach. So this concludes my brief presentation. Hope I gave you some insight on these two possible applications, and thank you for your attention.
Thank you, Simona, for your nice presentation. I think it's a different point of view. So far, we have been talking in this session about energy storage, and now you are talking really about an electrical system for electrical storage through thermal storage, because in your system there is in one case thermal and fluid storage, in the other case the Carnot battery is just thermal energy storage. So we have this integration of different elements. Now let me say, you have been working or presenting about CO2. Is the CO2 the only fluid that can be used in this kind of cycles, or is one of the best one?
Yes, of course, this is not the only one, because many other fluids can possibly be useful for, let me say, both the applications. All the fluids that can have critical point, but in general, changing phase near the ambient conditions can be possibly used in these for these applications, and so also eventually mixtures even of CO2 with other fluids. So this is not the only options. Of course, CO2 alone, let me say, could be easier to be implemented and less costly, less dangerous, and so the many advantages it has.
Thank you. I think you provided the guidelines, so to look at the critical point to understand the feasibility
yes,
of your batteries, let's say. Okay, thank you, Simone.
Thank you very much.
We can go to but keep warm for the final discussion. I also want to anticipate that along the final discussion, we're gonna also ask some questions for votation. So we're going to make a poll from the audience, and while the people will be voting, we'll be discussing about the same questions to see if the expert, let's say, judgment is the same as the audience judgment or not. So next speaker is the last one from my team, who is Dr. Matteo Cavo. Matteo Cavo is currently a PhD student in University.
Alberto?
Yes?
I'm sorry for interrupting, but I know Richard Boardman was going to present a little bit later on, but I know he's just a very tight schedule today, okay. So emergencies came up, so I was wondering if we can work him in while he's
yes, sure. So we, Matteo and Thomas, please wait. We give floor to Dr. Boardman, right? So Dr. Boardman is going to present quite, let's say, an innovative topic for our session and workshop, which is the hybridization of nuclear systems. And Dr. Richard is a leader in the INL Clean Energy Platform for Integrated Energy Systems Development. And I understand, Richard, you are leading a number of staff developing computational tools and test facilities supporting the design, assessment, integration, etc. of hybrid energy system at industry scale. So we are really interested in hearing from your nuclear perspective.
Okay, very good. Thank you for accommodating this schedule. We have another activity that suddenly came on my calendar and I couldn't avoid. So I've been coming and going between both meetings. I'm going to go ahead and share a screen here and take about 10 minutes, no more, and to talk about this area that you've introduced for me. So tell me if the slide deck is presenting here. Let's go ahead and share that.
Yes, we see that.
Okay. I'm going to put this in full screen mode here, but let's see if that works as well. Now, are you still seeing that screen?
Yes, perfect.
Okay, very good. So, yeah, I mean, you gave a good introduction, and I just want to make a simple point here that there is significant work going on by the entire international community on a whole new class of nuclear reactors. Some are called small modular, some are called micro reactors, and then of course there's the classical fleet of very large pressurized and boiling water reactors that are set up around the world. Approximately 200 of those, 100 in the United States. But the real question has been, could we utilize those reactors for the production of hydrogen, and so that they can participate in electricity markets in fundamentally a different way. So we've been doing work in this area, as you well noted, and just a quick shot here on somewhat of a timeline. We foresee that many of these reactors will be developed in the next decade and put down and be demonstrated. Some at the Idaho National Laboratory here in the United States. Some are already being built and operated in China. Russia's building some, as you're all well aware of, and several companies in Europe and the United States building these different classes of reactors, whether they be cooled with hot gas, helium, or cooled with molten salts, or cooled with liquid metals, or again, the typical water-cooled reactors. They all offer an opportunity to provide heat. And the point I want to make is not only is this heat zero emissions, but in most cases, it's already more cost effective to get this steam or this heat off of nuclear plants than it is to generate it with a packaged boiler. And I'm showing here costs in the United States, the green bars pointing upwards in 2021 and 2030, showing up to that diagonal line which is the cost of making steam, 1,000 kilograms of steam at about 5 megapascals. And this is US dollars and cost of natural gas. And the costs there for the blue bars are the costs in Europe. Now, we all know this may be a short-term phenomenon, but we may have recognized here recently those costs have jumped significantly. But the point I want to make by these dashed lines at the bottom is that the existing fleet and hopefully the advanced fleets are going to be able to compete in the production of heat. That's a key. So we want to say that this helps us look towards this Earthshot goal that our Secretary of the Energy has maybe been mentioned here in this meeting already, trying to get down to clean hydrogen for less than $1 a kilogram within a decade. And clearly that can be done with the blue hydrogen concepts which have been mentioned here so far. And it probably can be done with electrolysis when two things work together. So the arrow at the upper right-hand corner is the hydrogen and the fuel cell technology office. And also then there's the work being done under NETL's fuel cell program. These programs are really working to improve the durability and the performance of the electrolysis systems. And then in my case, I'm working with the Light Water Reactor Sustainability Program under the Department of Energy to bring down the costs. So what we're plotting here, if you see those diagonal lines, that's the cost of where it, the green line going up diagonally is the cost of where these systems would be. Once we get to high volume of manufacturing, that would be state of the art today. The blue diagonal line is where we hope to push the state of the art as we continue to do this research both under fossil energy and the EERE. And so the goal here is to compete against those dotted and dashed lines, which is the price of making blue hydrogen, but different with different assumptions on CO2 capture and sequestration. And the bar chart on the right shows how we have a waterfall progression towards getting to $1 a kilogram. And besides improving the stacks and increasing their durability, one of those objectives is then also to extract the oxygen. And so these integrated energy systems, oxygen may be important, and I'll take a moment to state that. I'll just quickly go to the next slides here. Trying to show how we can get to $1 a kilogram when these two programs work together. So we have a very strongly vertically integrated program here in the US. And again, I've mentioned the two programs that really contribute to this, fossil energy and the EERE programs, working all the way from fundamental materials development to improve the performance of the materials up to systems and integrated systems testing, which is what we're working on and collaborating with the NETL under the Hyper Lab, is to understand how these systems can be integrated in electrolysis and fuel cell modes and how they can participate on the grid. So we have a lab in Idaho. We call this our Energy Systems Laboratory, where we're integrating thermal energy production that can replicate a nuclear plant of different varieties and push that thermal energy into the electrolysis units. In the upper right-hand corner, you'll see our grid simulation environment, which we've been successful in tying back into the Hyper Lab and show how these two grid emulation environments can communicate and set up to look at how we can manage and dynamically turn on and off these unit operations in response to some grid demand function. So we have an opportunity here to test high temperature electrolysis on nuclear plants. There are actually 4 projects which have been announced, co-funded by the Department of Energy, and they're testing both low temperature PEM electrolysis and high temperature solid oxide electrolysis. And our objective here is to show that those large electrolysis plants can turn down 90% within 10 minutes, thus freeing the electricity to go back out onto the grid. And then they can turn back on and go into hydrogen production. So that begs a lot of questions technically and economically that need to be addressed. And so that's the purpose of these 4 projects I'm showing you here in these charts on the right that are up, and one will be done at the 9 Mile nuclear plant in upstate New York. Exelon is leading that one. Project will be done by Energy Harbor in Ohio. One will be done by Xcel Energy on a high temperature electrolysis solid oxide format. And then there was an announcement by Arizona Public Services to produce hydrogen and to convert that into synthetic fuels. And so that award was announced, and they're now in the pre-award negotiations. So our goal here in the integrated energy systems is not only to be able to coordinate with the grid, but to produce that hydrogen then when the demand is low for the nuclear or the thermal plant generation, produce enough hydrogen that we can support out a large number of industries. And where they would be located in a particular region, it may just be a steel mill, maybe ammonia production, but it could be providing this hydrogen down into the standard hydrogen fuel cells, and even for power generation, or for making synthetic fuels for a new fleet. So I just want to end with a couple of slides here in saying that we're working to see where this electrolysis can even support a blue hydrogen production, where the heat, the steam, and the oxygen that can come from splitting the water could be used to push it into a partial oxidation reformer. And so these are just some high view concepts here, even interfacing with a coal-fired power plant where the CO2 could be taken off to sweep the oxygen out of the solid oxide cell. And then that oxygen can be carried into the power plant to do an oxy-fired burning to just enable the CO2 sequestration. So our view is that when the nuclear power plants provide that heat and power, this is a system of substantial synergy. And then finally, of course, there's always getting into making chemicals and fuels. And so in our efforts under the DOE NE is funding us to begin to look at how these electrolysis platforms can also interface with the Fischer-Tropsch processes that fossil energy has been working on, as well as a number of industries. So there's probably some interesting synergies between heat integration and the fundamental hydrogen and oxygen integration. And this is just one potential schema. And so I guess I had one slide here also to discuss that not always is it taking and splitting water, but it's also potentially extracting the hydrogen from basic hydrocarbons like ethane and propane. And so we've been looking at the very same platform, or these high temperature electrolysis platforms, fueled by a nuclear power plant to abstract the hydrogen off of the alkanes to produce the alkenes, which are the monomers to make polymers. So that's my 10-minute kind of rush overview of some of the work we're doing at Idaho National Lab. Again, I want to point out the fact that our work in coordination with the Hyper Lab, Mike Tucker and his group back at NATL is important to us. And we think it leads to net zero campuses. We think it also leads to a pathway to utilize nuclear energy from micro reactors to large reactors. And I'll end with that.
Thank you, Richard, for your nice presentation. I would like to ask you about flexibility of the nuclear systems, but I don't have time, and but I only time for one question. So I take the question, since you have to leave, I understand, from Dan Maloney, who is asking, how does SOEC cost compare with the direct electrolysis of water? So maybe you can also answer on the flexibility question I had, since I suspect it's related to the way you manage electrolyzers in synergy with the nuclear system.
Well, this is a very important point that we have discovered, is that we can take advantage of the electricity prices when the cost is low on the grid. So there's what we have in the United States, the localized marginal price of electricity would be the price of the wholesale electricity market where that nuclear plant might be sitting. And now it has become the case that with the low cost of natural gas in the US and also with the advent of as much renewables coming onto the grid, there are situations in different regions where the nuclear plants can no longer actually compete and clear the market, as we would say. That is, produce electricity for the grid competitively during many hours of the day. So we have devised this schema where they would turn on the electrolyzers and produce hydrogen for a majority of the day, and then shift over to the electricity markets when the price goes up. And we've been working on some very sophisticated models with other national labs, and also with some of the modeling platforms that are actually developed at NETL to help us understand when these electrolysis plants will modulate between the electricity market and the hydrogen market. And it turns out when we do that, we're pushing the price of electricity down to an average cost of around $20 a megawatt hour. So we can make hydrogen very competitively and store it, even pay for storage during those periods. And the key is in the flexibility of these unit operations. Can we modulate those electrolysis units up and down as fast as we need to, which in some cases gets down to that 10-minute ramping rates that I was discussing. And then, of course, this plant is going to firm up the grid and provide capacity back into the grid when it's during periods of peaking or during periods of when just the price goes up, that it incentivizes the market back over to the electricity market. We're working with very specific utilities and very specific locations to understand these grid markets and to understand their opportunity to transfer back and forth between hydrogen production and making electricity for the grid. Now, and finally, to that matter, if we make enough hydrogen and we can store it, and for example, in geological storage areas, then we can turn around and burn that again in either a gas turbine, but interestingly enough, to burn it in reversible systems. And this is where we have a great interest in understanding the reversibility of the electrolysis units functioning in electrolysis, then reversing the polarity to run them as fuel cell units. So you're using the same technology to go back and forth between that electricity market and making and storing hydrogen. And in a recent study we just completed, we found that that's probably going to be very economic for many regions in the United States, particularly where there's a lot of solar energy, in making and storing hydrogen on a 6, 8, 10, 12-hour basis, then turning it around and burning it in a fuel cell system. And we're very intrigued and interested in the hybrid systems that are being developed. Why? Because of these great efficiencies we're hearing about, 70 to 80% efficiencies, which means that the round trip efficiencies overall of making hydrogen and storing it, bringing it back to electricity, start to become economically favorable. And our numbers are proving that out. So hopefully I answered your question, but I know I ran on quite a bit there.
No, thank you, Richard. It's clear you are very much on the topic. Thanks for an interesting presentation. Let me just make a final joke. I would love to have my hydrogen car. I would like to test your atomic hydrogen. Should be better than the green hydrogen. Will boost my performance for sure. But
yeah, yes,
just a joke.
Atomic hydrogen, that is good. Thank you.
Thank you. We are moving actually to the next presenter, who is Matteo Cavo. He's going to talk about the use of hydrogen on board of ships, and he's going to share his experience as PhD student of mine with a major international shipyard, which is Fincantieri, who is conceiving and now constructing the first world hydrogen ship powered by fuel cells. So Matteo Cavo, I think you are going to present a nice case for the green, or let me say atomic hydrogen exploitation. Please.
Okay, hello everyone. Can you see me? Can you see me? Can you hear me? Can you see my screen?
See.
Hello? Perfect.
Yes.
Very well, then let's start. Yes, I am Matteo Cavo. I'm a PhD student from University of Genova, and actually I'm going to present you part of my research, which is the feasibility study of PEM fuel cells and metal hydride coupled with for a zero emission ultimate ship. Let's get to the point. A small introduction. As everyone knows, 99% of ships is currently powered by internal combustion engines with conventional fuels. In fact, about 2.9% of global CO2 emissions is due to maritime sector. Especially we should focus on the trend of CO2 emissions, which increased more than 10% from 2012 to 2018. And this trend is very negative. We have to correct it. So we need alternative fuels and innovative technologies to invert this trend. Actually, IMO, in fact, in 2018, launched a new strategy which aims to reduce the CO2 emission by 50% by 2050 compared to 28. The IMO in 1997, in fact, introduced also the emission control areas to control the NOx and SOx emissions. Then the strategy is almost the same. We have to decrease this emission of the CO2. And here I want to show you how we try to focus on this theme and how we trying in Italy to move to a clean propulsion system for ships. There we see a project that we are really proud of, the TechVia project. This project is financed by Italian government, and it involves a lot of people, especially many companies like Fincantieri, Isotta Fraschini, Rina, and Cetena, but also a lot of universities like University of Genova and Palermo, and also Naples. Our goal is to develop and to build the first Italian hydrogen-based ship, which means that the base propulsion system is a PEM fuel cells propulsion system. This system is a 140 kilowatt power, nominal power, and the length of the boat is about 25 meters. So we decided to store the hydrogen with metal hydrate for a total autonomy of 8 hours at the nominal point, working point. And there you see the first first tried pictures of the boat that will be built in 2022. Let's get a little bit in the details on the topics that we are working on the most. There you see a basic concept of the propulsion systems. In fact, you see the fuel cell energy system, which provide the load for the boat, for the ship. And actually, we decided to thermically couple the fuel cells with the metal hydrate, which means that we want to recover the heat loss from the fuel cells and use it to feed the metal hydrate. In fact, metal hydrates need a heat amount of power to release the hydrogen. So the hydrogen goes to the fuel cells and the loop is closed. And you want to control and set this loop up. In fact, in your right picture, you see a little bit more in the details of the full system. You see the two branches of PEM fuel cells. Those fuel cells are heat up the water glycol cooling systems, which is the red arrows. And there you see two heat exchangers. The heat provided by the fuel cells is given to the water systems. The water heat up the metal hydrates and come back. So with the water C heat exchanger, we can release all the heat that is not needed for the loop. Actually, I would like to focus a little bit more on the control system, which is based on those sensors, sensors of temperature. In fact, we have to control the PEM fuel cells outlet temperature, and to do it, we have to modify the bypass opening valves. And then we have another loop to control the temperature which get out from the heat exchangers, those two heat exchangers. And this is very useful to maintain the metal hydrate temperature quite constant. We'll see some results after. I don't want to spend too much time on this slide since we are just see the description of the dynamic model, which has been developed in MATLAB Simulink, just to see the main hypothesis we used, the 0D models. We used adiabatic models toward the ambient, and also we decided to don't focus on the flow dynamics delay since we are comparing flows of water which is incompressible. Then this delay is really small. Actually, we decided to test a typical load profile. This typical load profile represents a typical trip of the Zeus ships, which goes from Ischia to Castellammare di Stabia. Those are places next to Naples. And there you see on the right the power ramp of the boat. we see that we have a 18 kilowatt power demand for the hotel load. Then we have 27 kilowatt demand for the maneuverment, and then 45 kilowatt demand for the 6 knots velocity of the boat. Then the results. Results show up something really interesting, since on the left we can see the amount of hydrogen discharged from the metal hydride, the powder. So we can see that this discharge amount is really similar to the consumption. Please focus that the consumption is not exactly the amount of hydrogen that get out. It's exactly the amount of hydrogen which get out from the tank. Then the discharge is the amount of hydrogen that the powder discharged. And then we'll see the pressure in the tank get lower and lower by time. But it always higher than the fuel cells pressure, inlet pressure. So we are always able to provide hydrogen to the fuel cells. And then the state of charge, for sure, never goes to zero. Another really important result is on the right, since we can see the PCT curve of the metal hydride. We see that we have a green isothermal for 51 Celsius, and we see the points which represent the working points for 30-minute steps. So we can see that we goes from almost 100% of state of charge to a lower state of charge, because we are using the hydrogen, but we always stay on the 51 Celsius isothermal, which means that we are able to provide to the metal hydride the amount of heat that is needed to discharge the hydrogen. So some conclusion. This model confirmed that the thermal coupling with the PEM fuel cells and metal hydride is possible, also in dynamic conditions. And also we can see the control strategy we developed is very suitable for our goals, and better performance has been obtained with 2 branches on. So we aim something for the future. For the future, we would like to validate this model using this use data, since the ship will be on the water in 2022, and also we would like to try to implement some other control methods, for example, using MPC to use smarter control functions. Also, we would like to include other components that are in the Zeus, and they just like diesel engines and batteries, in order to investigate the startup phase. So I think there you see some references for our work, so you can go there to get in details of the model. And finally, I would like to thank you everyone for the opportunity to present my research topic at the LEAD workshop. Thank you, everyone.
Thank you, Matteo, and the team working together with you on this very nice design of a hydrogen ship. Let me ask you a non-scientific question. So I understand you want to bring American tourists from Naples to Ischia. Now, when an American tourist will go onto the ship, will ask you, what about safety of this hydrogen ship? What can you answer?
Sure. Safety is something really important when we talk about hydrogen for maritime application. Hydrogen could be stored the most in tanks at high pressure, 200 to 200 bar. But the metal hydride solution is very useful to reduce the risk risk, since we can store this hydrogen to a very low pressure, about 40 bar, and we can store about 45 kilograms of hydrogen. Then it's very, very good very better than the common high pressure tanks. So
I think that the answer is right. Thank you. No, I think the technology makes sense. Metal hydrides on board of ship is an intelligent solution. So thank you for presenting this. Okay, so we can shift to the next presentation with Professor Thomas Heinz, Nice to see you, Comas, again, unfortunately in this electronic mode, but we live with that. Let me introduce you shortly, Comas. So Dr. Hines leads the US Department of Energy funded Georgia Tech Industrial Assessment Center, I suspect in Georgia Tech, and is well familiar with practicalities required for effective combined heat and power. You have been working on hybrid fuel cell system gas turbine cycles since very long time, one of the beginners, I would say, and you have been researching and teaching for more than 25 years on such a subject. You have been also collaborating with, since long time, with an ETL hyper facility at Morgantown, where you have been sending also several of your PhD students. Comas, the floor is yours.
Okay, thank you, Alberto. Can you hear me?
Yes.
Okay, great. And yeah, pleasure to see you, Alberto. I remember about a decade ago when you were having extended time up at NETL Hyper. So when time goes quickly, I remember that though. And likewise, good to see you, albeit virtually. And thank you all for attending. I see the time, so I will try to remain within a few minutes and allow for more details during the general Q&A. Normally, when you see this topic for a number of people in this audience, when you see solid oxide fuel cell gas turbine cycles, you know, the focus is on high electrical efficiency for good reason, because that is distinctly possible with these systems. But we're expanding the possibilities to now go ahead and say cogeneration as well, and not just high efficiency, but robust and efficient cogeneration, meaning having some type of ability to respond to variable loads, be it thermal loads, and of course power loads. So Nana, we can go to the next slide. And just a few slides. So first of all, on top right, I definitely want to thank the Department of Energy Efficiency, Renewable Energy Advanced Manufacturing Office, and in particular the Combined Heat and Power initiative led by Dr. Bob Gimmer. And what you see in this kind of busy diagram is a hybrid system. Some will call it a direct hybrid system, where basically it's a recuperative Brayton cycle, and in particular, you'll see a fuel cell stack that's on the high pressure side. So you're going to probably see that time and time again throughout this week. So I won't belabor it, but what I would do is just kind of draw your attention to another add-on to this, and that is if you look at the red exhaust coming out of the post combustor there, just following that, you see that red exhaust has a number of different duties that it traditionally serves. You see a heat exchanger at first encounters, and then it provides some more power by way of an expansion turbine, and then it may recuperate so you can do air preheating. But whereas in most flow diagrams it might be the end of its service, you see a last stop is that it actually winds up being a potential heat source for some type of cogeneration need. And that's what this project really focuses on, is when we expand the possibilities of these hybrid systems to now also include bottoming thermal loads. What could that, how good could we get, and what kind of dynamic response could we still have? So what we're basically doing in this project, I'll just kind of cut to the chase on, is that we're basically benchmarking the NETL Hyper facility and related simulations to look at what are the possibilities if you were to just try to do cogeneration without, as is, if you will, as the system is, you're just kind of adding a bottoming thermal load there, as you see. And in there, we're looking at steady state performance, but we are also looking at dynamic response as well. And of course, we still want to track electrical and cogeneration efficiencies, because one thing I'll point out is, cogeneration efficiency can be a bit misleading because you have two terms in the numerator, right? You have electrical power, and then you have process heating. You really don't know which one is contributing to your overall value. So I just want to emphasize, when we say high cogen efficiency, that's in tandem with high electrical efficiency. So at least a stretch target of 70% electrical efficiency, and then maybe 80% cogen efficiency by maybe say another 10 percentage points of process heating needs. So this is what the system would look like if you were to just kind of add a bottoming thermal load to hyper. But we want to also add a technology to it, and now you can go to the next slide. And that is, we are working with the University of Texas, El Paso. I know some are on the call even, Arif Bey being one. And we're working with them as a technology provider. And what they're doing is they're working on a high temperature recuperator bypass valve. So why do we want to do that? That being, we don't want all of the turbine exhaust to necessarily go through the recuperator on the hot side. We want to have the ability to detour some of it, to reroute some of it, to bypass the recuperator. And we'll go over why in some more details, but that is the actuality of what's being attempted here. So again, under UTEP's contribution, we're developing a high temperature valve to bypass the hot side of the recuperator. And we want to characterize that. We want to model how that valve performs at different settings as far as the opening and the mass flow rates that it permits. And then we want to insert this bypass valve into the cycle. So that leads to the next slide. And in the next slide, what you'll see is the same system, but if you look in purple there, there's now a recuperator bypass valve. So that's how it will look within the system, okay? And we're going to test that. We're going to model that, but then also have some aspect of physical testing of that on the NETL Hyper facility going forward. And we're going to benchmark the same things. We're going to look at steady state experimental performance, but we're certainly also going to look at the dynamic response. And here's the key here. What we're trying to really look at is the fact that if you were to try to have this type of approach, we all know that with renewable energy penetration and the like, an effective hybrid system has got to be more than just static. It's got to be dynamic. It's got to be robust against variable transients. And that's the key thrust that NETL Hyper has. So we're already tapping into that. But also even the loads themselves, right? In particular, the thermal load. It's not a given that you'll have a static thermal load. You can have dynamic thermal loads as well as dynamic power loads. And so we believe that by way of having this recuperator bypass, we basically have 3 degrees of freedom, okay, as I like to call it. And I'll use that as a way to go to the last slide. With the recuperator bypass valve, we're looking at 3 degrees of freedom. And Nana, you can go to the next slide. And that is the quality of heat that comes out of the exhaust, the quantity of heat that comes out of the exhaust to the thermal load, and even the timing. So when I say timing, that's if you look at the top left plot, if you were to take a typical coupled scenario where you didn't have a recuperator bypass valve, if you had variable power output requirements, and you probably would have somewhat shifted a very similar pattern of heat output because of the coupling there. But when we have a recuperator bypass, again, we can adjust the temperature of exhaust seen by the thermal bottoming load. We can adjust the quantity of heat seen by the thermal bottoming load. And with dynamics capture, we can also maybe even do some phase shifts so that we can have more control over our independent thermal transient demand, meaning that we're not rigidly coupled to the recuperator only, but we have a bypass that can allow for us to even change some of the cyclical timing as necessary to meet variable thermal loads. So we're on the forefront. Right now, we're working a lot with the technologies again. UTEP is developing a recuperator bypass. Garrett is on the call, a grad student working with me, and we're modeling the heat exchangers so that we can place them onto Hyper. And in that, we will benchmark what kind of efficiencies one might see. The speculative plot that you see on the bottom right are kind of these contours that one might see if you had different thermal bottoming loads for cogeneration efficiency, ranging from the upper 60s to the lower 80s as far as percentage is concerned. So the bottom line is hybrid systems, fuel cell gas turbine cycles, they can do more than give you high efficiency electricity. They can give you higher cogen efficiency with still high electrical efficiency. So you can kind of get the best of both worlds. But in order to do that effectively, we know that just like for hybrid systems focused on electrical power, especially in today's climate, you also have to be able to be robust for variable thermal loads as well. So we want to try to accommodate that by way of the recuperator bypass technology. All right, now I think that ends it for me, and I think we'll probably be ready to go into a general Q&A session.
Thank you, Thomas. Very nice bath back into the hybrid system, but also next speaker will be talking about that, so glad to hear again. Let me ask you a question. Yesterday we heard about China plans, the 5-year plan from 2019 to 2023 about SOCs, and I've not seen any specific item on pressurized hybrid systems, but I've seen a lot of activities on SOCs. So do you think we can expect some new Chinese hybrid system coming up in the next years? Or maybe not, maybe the topic is too complex also for Chinese.
Well, it's an international thrust for sure, and I think that's the value of even having a LEAP workshop, because we're going to need talent from all over the world. It's a very intriguing set of dynamics that one encounters, as Dr. Tucker could readily convey, and I'm sure he'll be reiterating this. Once you put these disparate systems together, a fuel cell with a gas turbine, different time constants. They don't necessarily behave intuitively as you might think they would when you combine them. And now, oh, by the way, add a third component. Now we're seeing a thermal bottoming load as well. There are a lot of rich dynamics that definitely come out, and it is going to be an international need for attention on this for us all to kind of collectively maximize this possibility. So again, I think that's the key even plug for the value of this LEAP workshop.
Okay. Thank you, Thomas, for your time, and we hope to have some time at the end anyway for some discussion. I anticipate we're going to do some extra time discussion because I see the time is finishing soon, and the regular time. Okay, so we move to the next speaker. Thank you, Thomas, again. The next speaker, I'm glad to introduce Mikais Agraniotis. Dr. Agraniotis is from Mitsubishi Power Europe that he joined in 2013. He's currently the sales manager responsible for decarbonization technologies, such as carbon capture and utilization and hydrogen production and use. But also, which is why mainly we thought of him for presenting here, and we proposed him, and we are glad he accepted. He worked previously as a product manager for Mitsubishi SOC and digitalization platform. So, Dr. Agraniotis, the floor is yours, and we look forward to hear from you about the Mitsubishi portfolio for decarbonization. And I know you have also some slides specific for SOC hybrid. If he is with us. Let's see. I got an exchange of email with him until 1 hour ago. So it should be there, but so maybe we can go to next presenter, and I will try to get in touch with him by email meanwhile. So Dave, indeed, you would be the last presenter of this session. So I propose you give your speech, and meanwhile I try to get in touch with Dr. Agraniotis to see if I can make him presenting here. So I think Dave does not need any. I mean, your presentation will be quite long, but let's say you are the leader now of LEAP. You have been the initiator of the LEAP workshop. So David Tucker has a background in chemical physics, if I remember correctly, and but also he's working in engineering since a long time. So he has a very broad scope and perspective for technology, energy technologies.
Okay, hold on. I gotta figure out how to switch the screens. Okay, Brian, you're gonna have to help me again.
You look good right now. You're full screen for me.
Oh, really? Okay. Yeah. All right, cool. All right, I'm sorry, guys. I'm I'm not so good with all this AV technology. So thanks, Alberto. Yeah, so you guys all pretty much know me, or most of you do. And yeah, I'm pretty much the hyper guy. So I just wanted to talk a little bit about the kitchen sink, and I really only have one slide, and that's this slide right here. So I appreciate the opportunity to talk about this. And Alberto, you can just kick me off as soon as your next speaker is available. But I wanted everybody on this participating in this meeting to think about the kitchen sink, because I think ultimately this is the direction to go. We've been looking at hybrids for a couple of decades, or at least I have. And our most recent ideas are, okay, yeah, let's combine the SOFC and the SOEC. I know Richard Boardman had talked about reversible. We're thinking about it more in terms of dynamic operability. So we're looking at, can we operate these things at the same time, where we're constantly generating power, recirculating the heat through the system, using thermal energy storage to handle dynamic loads and operations, using the pressure and the unutilized fuel to run an internal combustion engine for peaking loads, incorporating a receiver for concentrated solar power so that we can deal with the intermittency of solar energy right here in this thermal loop, right, passing through this thermal storage, which mitigates the transients, allows us to change the fuel that we use. Having an SOEC allows us to generate fuels that we can, maybe liquid fuels that we can store much more easily than say, pressurized hydrogen. Dr. Haynes talked about bypassing heat exchangers. So there's a lot of applications or a lot of potential for that in increasing the dynamics, the dynamic operability of the system. And finally, I know we've been in some recent discussions with Sandia about using small modular nuclear reactors to provide a constant source of heat. So when you think about, and I know that Sam Thomas presented in session 1 some slides to show heat sources and heat sinks. There are a lot of heat sources and heat sinks in the cycle, and electric sources and electric sinks in this cycle, and I guess chemical sources and chemical sinks. So if we had pretty much a constant heat source that just never varied, that would allow us to maintain temperatures in this cycle, under pretty much any, even extreme transient conditions. So my whole view, I guess my soapbox is let's integrate it all, and let's include everything, including the kitchen sink. If we can integrate everything, not after the electricity's been generated, but before the electricity is generated, we have a lot more options in dealing with transient operation. And I think it provides us a more viable path towards, getting to a world where we have 100% renewables, where we're not, using up fossil supplies, and carbon neutrality. If you want to get to the point where you're net zero, where you're not consuming, net carbon, I think this is the way to do it without breaking the bank, and ultimately having a system that's extremely flexible and can deal with lots of transient conditions. And really, that's all I wanted to say. Is I just want to get this out here, hopefully generate some conversation. I know I established the workshop hoping that there would be more interaction, but I know that we've got a lot of professors, and even folks from industry have professor inside them, and professors just can't talk in a short period of time. So, and I'm guilty of that as well. I talk way too much. So, but that's it for me. Here's my disclaimer. That's standpoint. I just wanted to bring that up, and hopefully Alberto is able to find his last speaker.
Yes. So thank you anyway, Dave, for your a little bit provocating presentation, and also we appreciate your effort in trying to assemble a layout which makes sense. I don't want to ask you about the cost of it. That's another. That's the imaginary world of Laplace. Laplace has the real world and the imaginary world. So that's a bit the Laplace transformation of the energy system. But we have now Michael Agranotis back to us. So Michael is glad to see you back on board. I introduced you before. So
sorry
for that. Everything about you already. So I give you now the floor for your presentation.
Yes, thank you very much, Alberto, and apologies for this problem. Let me share my slides, and I will try to be as brief as possible, because
no, don't worry, Mika. We give the same time, the same bunch of minutes to everybody, so we will exploit some extra time.
Okay, so thank you very much for the invitation for this very interesting workshop. My name is Michael Agranotis. I work for Mitsubishi Power Europe for our office in Duisburg, Germany. And I'm going to give you some outlook of Mitsubishi's technologies related to decarbonization. Starting and giving a very short overview, we belong to Mitsubishi Heavy Industries. We are part as Mitsubishi Power in the energy systems domain, and we have been also in very close collaborations with other companies within MHI Group. For example, one key company related to decarbonization opportunities is called MHI Engineering, and is a company who is the owner of the carbon capture technology and other technologies like methanol production, etc. Going forward, and just giving a very broad overview at high level, we would see that decarbonization includes several energy carriers, and hydrogen as also alternative carriers like ammonia are one key option, and primarily we all know there are different ways to produce hydrogen. We can differentiate between at least between green and blue, as you can see here. So green coming from electrolysis from the renewables, blue coming out from carbon capture applied in natural gas reforming plants. So at least these two options exist, and we see that at the end, all the decarbonization exercise is not an exercise of one technology, it is a whole value chain. So we need several technological items for every part in the value chain. So you see here from production to transportation and to demand. And for all these aspects, we need to have very competitive and capable technologies. And this is also our exercise within MHI Group, bring all these together and everything together. So just to give you an example, MHI has capabilities. So starting from the production of hydrogen, for example, on gasification or on offshore wind, also on handling hydrogen, also in matters of compressors, but also CO2, if applied in the industry, it can be used afterwards as a feedstock. So CO2 capture technology is also one key technology. And then going to transportation, also shipbuilding for specific carriers is one important topic. And also coming to the final question on utilization of hydrogen or other carriers, then the matter of applying hydrogen in gas turbines or in fuel cells becomes of a key aspect. So giving all this overall value chain overview, and going forward, I would like just to pinpoint some key items. So starting maybe from right to left, I'm going to show you some slides on hydrogen production technologies and carbon capture technologies, and then close this presentation with some additional information about Mitsubishi's fuel cell and Mitsubishi's hydrogen-fired gas turbine, and also some project examples related to the combination of all these technologies. So on electrolyzer, and I would just like to be very brief, Mitsubishi has established a partnership with electrolyzer manufacturer. It is a partnership already more than 1 year ago. Within this partnership, we try to build up a new generation of electrolyzers based on the pressurized alkaline technology, and also in the larger scale, so more in the scale of 10 megawatt. And as if you can see in the next slide, You can see here a kind of a typical arrangement of a smaller plant. And the idea is based on these building blocks and based on this technology to be able to scale up and use modules in the range of 10 megawatts, so that we can have in the future multi-megawatt scale hydrogen production plants. And this is the so to say the goal of Mitsubishi for the foreseeable future. Going one step further, carbon capture, as already mentioned, we consider carbon capture as one key item also on decarbonization. There are several technologies, several industries which are hardly to abet. So just to take as an example, for example, cement industry or steel industry or refineries. For all these industries, we consider that processes like amine-based processes, which are very known to the industry, are feasible because they are mature technology and they can be scaled up. Particularly, Mitsubishi has an experience more than 20 years applying this kind of technology, but with some very special characteristics. So mainly using its own appropriate solvent, which gives very high efficiency and low degradation and low emissions. And this facilitates also the deployment of this technology in large scale and also in a very high pace. And here you can see also the experience currently. One key project which is, I think, quite known in the US is the project, the so-called in Petra Nova, in Texas Petra Nova, which is actually the worldwide largest carbon capture unit ever built. It has a capacity of, and I'm just scrolling in the next slide. This is the plant which has been built in Petra Nova and in Texas, which has a capacity of about 4,700 tons per day. And the CO2 sequestrated there is used for enhanced oil recovery. So this is a kind of very concrete example, practical example how carbon capture can be applied already in the large scale, also in the current market conditions. And coming one step forward, what to do alternatively with the CO2? This is also another example. So in Europe, the discussion on utilizing CO2 together with hydrogen and synthesize towards new synthetic fuels, first of all, probably through methanol and then going to other fuels is one key topic. And for these types of developments, there are several projects in Europe already ongoing and in some first preliminary phases. One of them is also a project called North CCU Hub, where the port of Ghent in Belgium is mainly the leader and the coordinator, and several ideas how to build up infrastructure in that ports of Ghent are currently evaluated, and Mitsubishi is also participating in these developments. So just an example how CO2 use can be also effectively utilized in these kind of project developments. Going one step forward, because I mentioned to you that on the one side we have hydrogen production or sequestration of CO2 so that we can produce new types of fuels, but on the other side we have still technologies which needs to be in place so that we can utilize all these new carriers. And here is the example of the hydrogen fired gas turbine. You can see here, this is a typical typical outline of Mitsubishi's highest class of gas turbine, the so-called JAC class, which has on combined cycle efficiency of based on natural gas at first, an efficiency of more than 64%. And in principle, the idea which is currently followed, the development program which is currently followed, is to be able to convert or to develop a new generation of hydrogen gas turbines, which can be hydrogen ready. Let me say up to 2025. So this is the target year where most of the development programs aim to. And first of all, so depending on the technology or on the combustion technology, there are already some gas turbine models which are hydrogen ready up to a larger percentage, and as we go to higher, larger capacities, then there is a need to develop a new generation of combustors, and this is, as you see here on type 3, the multi-cluster dry low NOx combustor, which is currently under development, and this is one key technology item which will enable the use of hydrogen to high shares, so even up to 100% within the newest gas turbine classes, which will bring also the highest efficiency. So this is, so to say, a kind of roadmap for the development of the hydrogen-fired gas turbine. And
yes, exactly. If you can go through this last point, and then if you can go through.
Yes, I'm concluding through this fuel cell. I just want to say that the fuel cell technology is already an established technology. The key item, it has a very high flexibility, so the same model can use from natural gas up to 100% hydrogen with a very high efficiency. And maybe just to give you an update, I'm scrolling through the slides. I think this is the key update. This SOFC is already, we have several references in Japan, and we have also one reference in Europe. So this is a very concrete example how decarbonization could look like at a decentralized scale. So fuel cell, Mitsubishi's fuel cell is a unit with a 250 kV up to 1 megawatt. So it is a very concrete example how to decarbonize the power generation sector on the small scale. And with that, I would like to conclude my presentation. Thank you very much.
Thank you, Michaelis. So we came to this final part of the session. Actually, we are 10 minutes late. So I shortened the original program in this way. Let me recover one question that remained pending to Tommaso and Justin about the thermal energy storage. Tommaso and Justin, you can read the question in the chat. Was written at 5:26 p.m. Regarding basically the active power from the thermal energy storage. I suspect it's they relate to, you know, to the thermal power, how they can really react to, you know, to the, how they can be flexible, let's put in these terms. And also they want to have some estimate about the cost per kilowatt hour. I suspect to have a comparison with the batteries, which are well known in terms of cost. This is just to, so think of the answer, but finally I will just make a question to all the panelists, a little bit political question, and then you can answer giving your opinion to that. So Justin and or Tommaso, can you answer to Mr. Arish question?
Yes, Tommaso speaking, and thanks for your question. And okay, let's start from the estimation of the cost of thermal energy storage, like the ones I've shown. It depends. The cost depends definitely on the phase change material, because, for instance, as already mentioned during my presentation, the initial idea was to use paraffinic-based phase change material that is quite expensive and also don't have a very good thermal properties. And in this case, the cost is around $370 for kilowatt hour. While by using the water, okay, the cost is essentially just the equipment cost, because obviously the water has got a negligible cost, so, and also got a higher thermal property. So in this case, the cost dropped down around $130 for kilowatt hours. Obviously, in this case, you have also to add the capital cost of the heat pump in order to make the overall system integrated in an more bigger system. And for what concerned, the other question was, how quickly can you ramp up or ramp down the active power from the test? Okay, this in charge mode, this depends definitely on the characteristic of the heat pump with which the thermal storage is coupled with. And but for what concern the discharge mode, but I think this is quite more interesting. Operational mode, and this depends on definitely on the load, on the state of charge of the thermal storage, but also okay, as already said, we vary it by
try to be quick.
Okay, sorry.
The answer is
in our case, it's about 2-3 minutes from maximum to minimum load output.
Which is a lot, very, very fast. Thank you. That's an important information for the floor. Justin, do you want to add something?
Yes, I can briefly add on to what Tommaso explained. So the cost of the storage materials depends largely on the material, as it was mentioned. I would say you can go down from $70 per kilowatt hour up to this $370 that was mentioned, depending on the grade. The purity of the material, of course, and then that would be like the installed capacity, and then for the usable amount of the cost per usable kilowatts hour that is actually being supplied, delivered to the users. I would say depending on the tariffing system, you can actually go down quite low to the off-peak pricing. So that's the advantage of having the storage. Yeah, thank you.
Thank you, Justin. Okay, so the final round to each of you is the answer to the question that I just posted into the chat, which was supposed to be a poll, but we just do it a round table shortly. So I ask your vote. So the question is, of course, in this case, a little bit of motivation. The question is, what's going on now? Things changed in my, okay,
Alberto, I opened the poll so they can actually read the questions and enter their
the poll. Okay.
Yeah, you have about 3 minutes.
So the poll is open to everybody, understand? But I asked the panelists only to talk about the last question, which is, do you think we need an energy apocalypse to tackle the current energy targets for 2050? Yes. No. I hope the targets will be moderated or reduced. So let's start from the first speaker. The first speaker today was Tommaso. What do you think, Tommaso? What do you vote and why? You are muted.
Sorry, Alberto. Sorry for everyone. I'm a little bit pessimistic, so
You're still muted.
Can you hear me now?
Yes.
Okay, sorry. I'm a little bit pessimistic, so okay. But I will vote the third response that you said. I cannot read your question anymore. I don't know why, but okay.
So you vote for, let's hope they will be moderated. Thank you.
Yes, definitely.
Justin.
Yes, I was reading through the poll questions. From my perspective, I would say, I mean, the cost is one major issue. If we can because the technology is out there, if we can overcome the costs aspects, I think we'll have a bright future.
So what do you vote then?
I would say that currently the cost is too much for the storage technology. Of course, it depends on, it's very case specific, but if we want to have it everywhere, on the grid, on the network, on the utility company side, on the user side, I think it's still very case specific.
Okay. Yeah. Okay. But okay, thank you, Justin. But let me repeat the question. The question is the last one. Do you think we need an energy apocalypse to tackle the current energy targets for 2050?
Okay.
Don't look at the pool is a little bit confusing now. Okay, so let's go to the third then. But maybe Justin, you think of it and you give me your vote later back. Simone, what do you think? We need an energy apocalypse or not?
Honestly, I don't know. I hope not. That it will be not necessary because everybody does not want it. So honestly, I don't know. I hope not.
No. Okay. So you know because you hope not. Thank you.
Yes.
Yeah. Matteo had to leave, but we can ask the question to Comas.
No, it reminds me of putting on brakes gradually or putting on brakes in an emergency. And if we as far as just this abruptness, and I don't think we'd respond well. I think it would prompt us to have to do some things, but I think we'd be scrambling at that point. So no, not that. But it does need to be done more effectively.
So you are more for, no, we can improve things gradually. Okay, thank you. Michalis Agraniotis, what do you think? Are you with us? Probably not. Dave, what do you think? What do you vote for? Do we need an energy apocalypse or not?
So if I thought we didn't need an energy apocalypse, I wouldn't be hosting this meeting. Obviously, I think so.
So you say yes, we need an energy apocalypse. Thank you.
There's no question in my mind. Those are pretty aggressive goals. Normal technology development paradigm requires 20 years for a new power system to realize commercialization. So, to try to get to complete no carbon being used or just by 2050 in anything, transportation, energy, every sector, yeah, you need an energy apocalypse for sure.
Okay, and Justin?
I think we are shifting progressively. I'm more optimistic. I think it will be difficult to shift towards 100% carbon-free society, but we are working on it, and that's also why we are all here. and I feel positive towards it. I think we will move progressively towards a carbon-free future, definitely.
So you think we don't need an apocalypse? Okay.
I would say maybe gradually, little by little, small apocalypse, but not a big one, not a devastating one that would destroy the whole society.
So I think the majority kind of voted for no or better. We can do it. Okay, we can do it. Yes, we can. Yes, we can. So I understand the message is a little bit this one. And so I thank you again, everybody, for your presence. the audience, one side, but especially the panelists for their active participation and presentation. I'd like also to thank NETL for having organized all this workshop that will continue till the end of the week. And please continue to respond to the poll that has been published now. We will collect the results for writing the final technical note of this workshop. Thank you, everybody. Have a good lunch or dinner.
Thank you.
Or dinner, yeah, dinner in Italy, I guess, lunch for everybody else. So we will start again in, I guess now just a little over half an hour. There will be breakout rooms available if you want to sit and chat during your lunch, dinner, or if you just want to, get up and walk around. And hey, hopefully we'll see you back here in 35 minutes for dynamics, because dynamics is fun and exciting. So thanks very much, Alberto. I appreciate it greatly. And thanks for all the speakers. You guys did a wonderful job. So, all right, we'll see you in some minutes. And I think when Brian puts up the breakout rooms, you actually can click on it and see who's in the room, in each of the rooms. If you need to go talk with some guys you haven't seen for a long time, as Nana said, if you need to socialize, please feel free to take one of those breakout rooms and have a discussion.
Yes, they're available now. So if anybody wants to step in, you go up to the participants window and there's two options. There's the main meeting, you'll see all the participants, and then there's another option that's for breakout sessions, and you can join whichever of the rooms that you'd like.
Can you hear me?
Yeah, we sure can.
Yes, it means my audio is good now. Just wanted to let everyone know that this meeting is considered as an open to the public meeting, which means all the information included in your presentation and discussion should be public available before this meeting. If you have sent your slide to me, then you are good to go, because we posted the slides online already, so it's considered publicly available. Another thing is the entire workshop will be recorded. This is because we are going to write a technical note after the workshop, and the technical note will be available for all the attendees when it's available. And we suggest you to turn on your camera when you are presenting or when you are asking questions, so that we know who is talking. And since we have many people on the line at the same time, please mute yourself except when you are talking. And if you have questions, you can post those questions in chat while the presentations are going on. Or during the free open discussion, you can ask your question to the presenters. That's all.
All right, thanks, Nana. So we're going to then get started with this next session, which is on dynamic performance of hybrid power systems. So, and it's my honor to introduce Dr. Jack Brower, who's professor of mechanical and aerospace engineering. Is that right, Jack?
Yes.
That's what it says. Okay, and director of the National Fuel Cell Research Center and the Advanced Power Energy Program at the University of California, Irvine. So Dr. Brower has been involved in hybrids since as long as I can remember. So that's at least a couple of decades.
Perfect, exactly.
And probably more, but I won't say how much more.
I think it's maybe only 22.
22, okay, all right, cool.
22 years.
So he's in the world in hybrid, and his group has done more modeling studies of system dynamics for hybrids than any group I know of. So and he is gonna chair this session for us. So thanks very much, Jack. And with that, I'll let you take it away.
Thank you very much, Dave. And it's been my honor to know you and to work with you on a number of occasions, and with US Department of Energy support in so many efforts along the way in hybrids. And thank you for this opportunity to speak here today. I'm going to talk about hybrid system dynamic operation, and I'm primarily going to present on work that we've done recently with my colleagues, Dr. Luca Mastropasqua and one of my graduate students, Gi-Jung Lee. But I'm starting with the fact that we have here at UCI been studying solid oxide fuel cell gas turbine systems for more than 20 years. And these are the highest efficiency fuel generation systems that are out there. Can't beat it with anything. And we've been fortunate to partner with so many awesome entities along the way, including Siemens Westinghouse, Southern California Edison, Southern California Gas Company, Fuel Cell Energy. And from the very beginning, this is data from a system that we started testing in our laboratories in 1999. The world's first solid oxide fuel cell gas turbine system shown here. Going to my laser pointer. Shown here in our laboratory. We tested that between 1999 and 2003 with Siemens Westinghouse and Southern California Edison. We also worked with Fuel Cell Energy over the years in all kinds of hybrid fuel cell gas turbine concepts, including carbonate gas turbine hybrid concepts as well. We've also spent in more recent times quite a bit of time looking at whether or not these could be applied to locomotives, okay, instead of the diesel combustion-based systems. Of course, if you're operating them on a train, they have to be highly dynamic in their operation, as you can see with regard to a switcher locomotive or a long-haul locomotive demand here. This also is shown in this simulation that we made of a hybrid fuel cell gas turbine system powering a locomotive pulling 10 freight cars up the elevation, as you see on the left here, from Bakersfield to Mojave, a known central California to desert route. And you can see here that the locomotive power demand is highly dynamic. But that's not the only reason we need dynamic operation. As a matter of fact, the grid in the future also is going to need dynamic operation in order for it to accommodate the renewables in the grid. And you will see that we are doing some work recently led by Fuel Cell Energy with partners Brayton Energy and us with funding from ARPA-E, and that's the main project I'm going to talk about. It's called Adaptive Solid Oxide Fuel Cell for Ultra-High Efficiency Power Systems with funding from ARPA-E. And here you can see the plant layout that we have. It looks a lot like many of the systems that I think you've already seen presented here today, but has, of course, a compressor, centrifugal turbine. And of course, this compressor feeds air with preheat into the solid oxide fuel cell. We also have fuel that goes into the system, natural gas, where it is desulfurized, pre-reformed before it goes into the solid oxide stack. It's only pre-reformed partially because we desire some internal reforming, and you'll see in the temperature distributions that I show later that we do indeed have internal reforming, and the rest of the balance of plant shown here. And when we operate this on 100% natural gas at the reference operating conditions, you can see various aspects of the simulation. You can see here that we end up having about 0.87 volts that we're operating at. We have about 485 milliamps per centimeter squared as the average current density. Fuel utilization on a single pass is only about 65%, but we get about 85% overall because we have some recirculation. And then we get some micro gas turbine input or solution characteristics that you can see here. And we get then, as a result, the overall performance and efficiency that's about 72% fuel to electricity conversion efficiency. But now we need to operate this system dynamically. And so what we have developed for the main control strategy is shown here on the left, where we have the control loops identified, and we are manipulating certain variables to control certain variables. So we manipulate fuel flow to control the fuel utilization. We manipulate current to control the power of the fuel cell. We manipulate the RPM by applying various loads to the gas turbine generator to actually control the outlet temperature of the cathode. Essentially, the RPM determines how much air gets into the cathode. Then we have a fuel cell bypass valve that we manipulate for the cathode inlet temperature control, okay? And then we use excess fuel to control the turbine inlet temperature. And you can see the various set points where we're trying to get about 993 K for the outlet temperature, 998 for the inlet temperature, 1105 for the turbine inlet temperature, etc. And we've shown using this control strategy that we can actually dynamically operate this safely all the way down to 15% while maintaining efficiency, especially at full load, that's greater than 70%. And what you can see here is that we are manipulating the power in various steps where we move it down pretty quickly to about 20% of, or 15% of full load. And you can see here that we have the cold air bypass temperatures that you're showing here. We have the efficiency that is shown in the dashed line here, and you can see under nominal conditions, we're getting above 70%, but even out all the way down to 15% of nominal power, we're still at about 50% fuel to electricity conversion efficiency, and we can operate this dynamically. However, when we have to go all the way to startup or shut down, okay, so all the way to 0, we have to implement control a little bit differently. And in particular, we have found that you must manipulate the fuel utilization set point in order to actually maintain control all the way down to 0. So when we do this, we can go all the way down to 0 load, okay, in various steps. But what you can see is that we actually change the global fuel utilization. That's shown here in the black, starting at this point here when we get to about 15% of full load. And then we decrease it again as we go to lower and lower set points, okay, until we can actually turn this all the way off. And then we can start it back up. And you can see we are doing this with safe operating conditions by manipulating those variables that we showed earlier. We also then can show how we can use these kinds of hybrid fuel cell gas turbine systems to complement sun and wind power. So what we are showing here is that on a sunny day, we operate at full power in the early morning and at night, but we can follow the load profile of the sun by turning down the hybrid system so that it's at its lowest operating condition, lowest power output operating condition in the middle of the day when the sun is shining, and then come back up at night. So we can perfectly complement both a sunny day, but also a cloudy day, as is shown here, where we have clouds that interrupt the solar power, and we can manipulate the solid oxide fuel cell gas turbine system to follow that. You can see also here what happens to the cold air bypass and recycle valves. We actually have to manipulate them, but we maintain efficiency also at very high levels, between 70 and 50% for the entire day, operating in complement to sun power. We can also complement wind power, and that's what's shown over here on the right. And again, you can see that we're following dynamic dispatch when the wind is blowing, as it is here in the early morning hours. We can turn it down when the wind stops blowing in the middle of the day. We can follow that wind profile. And for all relevant operating conditions, we were able to keep electric efficiency greater than 45%. So it's pretty remarkable that we can do this to complement renewables. We also are investigating whether or not we could mix hydrogen into the natural gas system and then use blends of hydrogen and natural gas in this very same system. As a matter of fact, we are trying to see if when we start to do this in the natural gas system, whether or not this system could operate on mixtures of natural gas and hydrogen up to 70% hydrogen without manipulating the design, right? So we want this to be robust to this partially decarbonized gas. And you can see here we have slightly different steady state operating conditions at 70% hydrogen natural gas blends. So our voltage is a little bit different, our current's a little bit different. We have a single pass fuel utilization that's higher, okay? But without changing the design, just controlling the fuel cell the way that we were controlling it before, we can actually operate this system all the way up to 70% hydrogen mixed with natural gas. And I'm showing here the simulation of the 2D unit cell. And what you can see is that depending upon the amount of hydrogen that we have a different temperature profile of the positive electrode, electrolyte, negative electrode pen in our system. So we have, for the case with natural gas, we have higher average pen temperature with hydrogen blends, but lower maximum pen delta T, okay? And that's primarily because if you look at what happens when we have natural gas, we end up having cooling at the inlet of the cell due to the internal reforming that happens. And that leads to a higher delta T in the natural gas case. The current density gradients end up being higher though with hydrogen blends, but they have similar average current density as you can see in these plots. Finally, you can see as a function of hydrogen content, that's what the x-axis is on all of these plots, okay? What happens when we increase hydrogen is we see an increase in cathode outlet temperature. Again, primarily because we don't have the cooling of internal reforming that happens. And we see that voltage drops slightly as we increase hydrogen content. And you can see that the TIT increases slightly, okay? And finally, you can see that the net electrical efficiency drops as we add hydrogen up to 70%. But it still remains above 70% fuel to electricity conversion efficiency. And importantly, what you see here is that when we partially decarbonize the gas that goes into this hybrid system, we can dynamically dispatch it with much lower net CO2 emissions. We go from about 280 kilograms per megawatt hour to about 150. So dynamic operation of these hybrid systems, I think, is very important for our renewable future. It's also important for interesting applications like locomotives and ships and planes and things like this, if we ever want to put them on those technologies. I also think it's going to be important for us to be able to operate our future systems on mixtures of natural gas and hydrogen, maybe even pure hydrogen in the very long term. So thank you for your attention. And want to see if there are, should I ask for questions at this time?
So that's up to you, Jack. As you can ask for questions, or you know, we've told everyone that they can put questions in the chat,
okay,
which you can check after people are done talking.
Okay. So in my schedule, I have Eleonora Gaducci next, and did she join?
Yep, I see her.
Yes,
So,
I'm here.
Eleonora, can you show your camera and share your presentation next, please?
Yes, of course.
Nice to see you again.
Nice to see you too again. Yes, so here is my presentation. I hope you see it. And
it's working well. Thank you.
Okay. So yes, I think Professor Brower already knows something about the system I'm going to talk about, but today I'm going to give a more detailed overview of the dynamic performance of the high-C system, which is installed in the laboratory of the University of Genoa. So a short overview of the laboratory itself. It's a 200 kilowatt size system complete with the balance of plant components, and it is made up of 8 polymeric electrolyte membrane fuel cell stacks supplied by Nuvera. So they are sized 30 kilowatt each. They are divided on 2 parallel branches, and the project has been sponsored by Fincantieri. So it aims to actually assess the employee of the technology for shipping applications. So in fact, the balance of plant is simulating the installation on board the ship with a 2-level cooling system to simulate the heat exchange with seawater at constant temperature. And the other components are an industrial compressor to simulate the connection to the compressed air line on board the ship. Then there are also a dryer and filters, a modular resistive load through which we simulate different load profiles we want to test, and the hydrogen is stored in a compressed form at 200 bars. So regarding the experimental activities, the main question we wanted to answer to with this test campaign is how does a complete fuel cell system behave in dynamic operation? Because literature is a bit lacking about the whole system examples. So first, to assess the dynamic performance, we tried to implement different ramps dealing with current. For example, here we can see 2 ramps implemented on the system, starting from 10 amps and reaching 130, then from 10 to 160, considering that the maximum current reachable is 250 amperes. So as we wanted to test what are the actual performances of the system compared to the ones prescribed by the fuel cell supplier, because of course things change when the modules are inserted in the whole system. So the first thing we notice is that as the system is built, depending on the base load, it is possible to reach different power outputs in a second. So the higher power steps are reached when the base load is lower. And this is due to different reasons. From one point of view, there is the control strategy influencing this behavior. So as you can see here, the reactant flow rate, the red line, is delayed. So the adaptation is delayed with respect to the current variation. And this is due to the control strategy that regulates the other parameters depending on the current. But also, why do we reach higher power steps starting from low base loads? Because we have increased the airflow rate at low power outputs, and this was decided together with the fuel cell supplier. So once we defined the main dynamics of the system, we tried to implement an operative profile, and this was chosen together with Fincantieri. And it wants to simulate different conditions, so it alternates more dynamic operation variable load to a more constant load operation. And this is interesting to simulate maneuvering and constant speed propulsion. So in this test, for example, well, first of all, as you can see, the blue line is what we actually implemented on the system, because considering the dynamics, we adapted the load profile to the actual ability of the system to load following. And in this case, we were simulating also a fault condition. So branch 2 is operating with 4 stacks, but branch 1 is operating just with 3. The NDDC-DCs are bypassed, so the system is directly working with the modular resistive load. And in this condition, in this configuration, the system can follow the load profile successfully for the hour which was in which it was implemented. But of course, there is the first comment is that the load profile has to be adapted to the performance of the also of the balance of plant components, and that still there is some variability in the boundary conditions that can influence the performance. Here, for example, there are the influence of both the compressor behavior and of the analytic purges. So this must be taken into account. Last, we wanted also to test the operation of the system in employing this time the DC-DC converters to equalize the voltage output at on the two branches. So here, for example, we ramped up the current gradually from 0 to 230 amperes, so almost 90% of the current. And of course, the voltage is varying coherently with the load. And the voltage output of the two DC-DCs is correctly controlled. This control strategy that involves the DC-DCs, of course, as we can see here, is more, it is safer from a certain point of view, considering that the stacks, the fuel cells can age differently depending on the operation. So in this way, it is possible to split the load considering the state of health of the cells. So as a conclusion, I would like to underline that it was possible to test a complete system, which is quite innovative in dynamic conditions with different load profiles. And the main output of this experimental campaign is that it is not only important to study the dynamic performance of the cells themselves when they are just were operating on their own, but it is important to consider the balance of plant performance. So the main question that can arise from this presentation are which components are we going to employ in the future as a balance of plant? So do we want to prioritize the costs of the system, employing more commercial components, or do you want to prioritize the state of health of cells? And then, of course, it has come time to define control strategies that consider the balance of plant components and also the configuration of the system, considering that you can have both a series and electrical design. And last but not least, considering that even at constant load, there can be some influence of the balance of plant components. When will it be advisable to employ the PEM fuel cell system as a power generator? For which applications? So with this, I would like to conclude my presentation, and thank you for the attention, and I am open to questions, of course.
Thank you very much, Eleonora. Do we have questions for Eleonora? I looked in the chat as you suggested, Dave, and I don't see any there, but I don't know if that's how you've been receiving questions from people who don't raise their hand.
Hello.
Yes.
Go ahead, Ben.
This is Ben Corpening. I have just a quick question. At a glance, it looked like you were running the PEMFC stacks at about 25 kilowatts output, although there are 240 kilowatt nameplate. Any thoughts on how that would affect the dynamic behavior since you were running at such a low load factor?
No, the graphs I have reported were specific for the single stacks. So the whole system is 240 kilowatts, that's correct. But the single stacks, which are 8, are sized 30 kilowatts each. So that's why I just reported the figures for the single stacks, maybe just to be more clear.
Thank you.
Thank you.
It was operating roughly at full power, right?
Yes, it was indeed. During the first operative profile tested I was showing, we were simulating the fault conditions, so 7 stacks out of 8. So also this difference between the two parallel branches, which is interesting to be studied because, of course, faults can happen. And the other test we were running it was 6 stacks out of 8, so 3 and 3 on the 2 branches, and we were reaching a power output of 180 kilowatts. But we also run the tests with the complete system, of course, running. But I thought it was interesting to see also at partial load how they could behave.
Very
So,
nice. Go ahead.
Sorry, Eleonora, I just wanted to ask a question about, I mean, you surely went through that presentation very fast. So you are you're the only presenter, I think, so far who's been just right on time or maybe even under time. So, but you were going through it so fast that it was hard to tell what kind of ramp rates were when they were changing power quite quickly. But what kind of percent per second or percent per minute, or what kind of rate changes did you?
When we performed the initial dynamic tests, we were trying to have ramp in a second. So we were increasing the current, for example, 100 amperes per second, then 120 per second, and see how if the whole system could manage this current this load variation. So this was per second.
Okay. Thank you very much. Grazie mille.
Prego.
You are to be congratulated for actually even getting the system to operate after it had been sitting around for so long. And so really cool. Also, I think that the marine application is a very, very important one. So really cool that you have this effort underway. May I ask, do you think that solid oxide may have some applications in marine? Or do you think it's only going to be PEM?
No, I think in the next future it will be PEM fuel cells. But because there is a lot of research on the topic, and it's for sure it is easier to implement more dynamic load profiles. But in the next future, I mean, in the medium term, I could guess that also solid oxide fuel cells will be necessary for shipping applications because of the large size needed. Just there are a couple of reasons, but I think they will be also there will be also solid oxide fuel cells in the maritime field.
There are some companies out there that are investing in that option. I think in particular, if you think about the possibility of using liquefied natural gas or liquid methane, which has a higher energy density than liquid hydrogen, there's an interesting way in which solid oxide would have an advantage because it can handle the methane.
Of course, yes. That's one of the most interesting part of solid oxide fuel cells, of course.
Yes. Yeah.
And sorry, hi Jack. I may have a thought for your questions. So personally, I think solid oxide fuel cell may be better for the marine application because for PEM fuel cell, I believe this lady tested his stack on the land, correct? Did you do it on the sea?
In the high sea laboratory is on land, but it's trying to simulate the installation on board the ship.
Right. My point is from the viewpoint of mass transfers. So the air relative humidity on the sea may be very high, like 80 or 100%, and you may see like this very high humidity will have some bad effect on your PEM fuel cell cathode. You may have cathode flooding there, which will significantly change your dynamics. That's just a thought.
Do you want to answer the question? Or?
No. Please go ahead, Eleanor.
Okay. As far as regarding my experience, at least, I saw different control strategies, even relating to the humidity inside the cells. For example, the stacks we employ, they are auto-hydrated, so the humidity is balanced with through the thermal circuit actually. So we do dehydrate the cathode flow before it enters the fuel cells. So I don't think the humidity could be a real issue on board a ship, because you can also have other components and usually the stacks are closed. They are inserted inside a protection, so the environment air should not affect too much the flooding.
I agree, Eleonora. I think that PEM fuel cells have a bright future in marine applications. A lot of people are pursuing them. Well, please help me thank Eleonora. It's late where you are, so thank you so much for presenting today.
Thank you for inviting me.
Yes. Next, Dave, should we look for Professor Rory Roberts? Is he on?
Yeah, I'm here.
Hey,
Hello.
sweet.
Let me go ahead and get started next.
Yeah, let me please introduce Professor Rory Roberts, someone that I would like to see in person again soon, having been a mentor and colleague of his for many years. Thank you so much for being here, Rory, and go ahead.
Do you see my main slides to make sure I'm not giving the presenter view?
We don't see the slide. What we see is a blank screen that has the WebEx symbol on it.
Oh. That change?
No.
Okay, let me change my share. Okay.
That's more promising. We see the whole screen right now. Yes. And if you just go to display settings and flip that, then.
Okay. All right.
That's perfect. Thank you.
Okay. You never know which screen. When you have 3 screens, it's way too many. So yeah, well, thank you for the introduction. And I'm glad to be here and invited to give this talk. And yes, I definitely love to see everyone in person and here. I don't think I even shared my camera, but I may have used too much time to do that. I'm probably going to segue into something a little different. Some of our work here lately, I've done quite a bit of aerospace work in the last decade, and I've had a background in solid oxide fuel cells, both for my dissertation and through my industry experience with Rolls-Royce. But my talk here is going to be more on a carbon neutral aerospace hybrid electric propulsion system. And what I'd like to, there we go, just to kind of give some insight and things about if you consider electric propulsion at the large scale. And when I'm saying large scale here, it's something on a 737 Boeing class type aircraft, single aisle, 180 to 200 passengers. And when you're going to that level of electrification for an aircraft, there are lots of challenges. So you're talking about 30 megawatts of electrical power. And in order to make this happen, there's several things that need to occur. One, you need to have very high conversion efficiency, because the ultimate goal to the airlines is dollars per passenger mile. And then also is driving, net zero emissions is another thing for the transportation sector to start addressing the energy and emissions and carbon and the energy consumption in the transportation. And plus, you need to meet the current fuel storage requirements, which is you only have so much volume on the aircraft, and you can only have so much weight because you are very, very weight constrained on the aircraft. And this requires basically a vehicle level top-down design approach and how you're going to integrate these systems, because not only you have to produce power, but you have to have a very responsive dynamic system for power generation. And this requires also very high power density electric centric systems. And so how are you going to produce electric power production? And RPE actually put out some programs to address some of these challenges. And we were fortunate to have a project in each one. The REACH program is addressing the power production. The electric propulsors, mainly the electric motors and thermal management is covered by the Ascend program. And then how you can distribute 30 megawatts of power around an aircraft. And that's being addressed with the cable program with RPE. And one thing to note, and this is a little sidetrack, but you have hundreds of kilowatts of low quality thermal management that's required because these electric devices, you're talking 30 megawatts of electric motors, you have to be able to cool them and maintain high power density within those technologies. So some of the really good, challenges of the aircraft application is you have to operate at 35,000 feet. You're talking about 23 kilopascals, which is about 1/5 the atmosphere we have here at sea level. So you have a vast range of operating loads and pressures and temperatures. So this is really demanding not only on load, but what's going to be coming into your system. What are the boundary conditions of your, say, inlet compressor, the hybrid system. So you need to provide a high power density, high efficiency electric power generation system with some thermal management aerospace systems, thermal management to help assist with the aerospace system. And so here you've seen some hybrid systems that have been presented today and yesterday. And what I put here is probably the most generic one, fuel cell hybrid system. And the fuel cell hybrid system, as Jack alluded earlier, is the most efficient system out there thermodynamically, at least from just a topping and a single bottoming cycle. But so it's perfect for the chemical to electrical conversion efficiency. And it also provides a pressurized environment, which you must have if you want to operate at high altitudes. Operating your fuel cell at 20 kilopascals may not be, would result in very low power densities. But some of the biggest cons here are, it could be a very massive system with very low specific power, kilowatts per kilogram. It has a very large thermal mass, possibly. That results in sluggish response to any perturbations as your temperatures and pressures and load are changing coming into the system. Could require long startup times. Don't want to wait a day to start up the aircraft and warm it up, or hours. And it typically requires complex thermal management with a lot of valves. And on top of that, hot valves. Hot valves are large, can be expensive, can provide maintenance issues. So what we've done as part of our RPE REACH program is propose an integrated propulsion, power, and thermal management system. And this kind of reaches across all three programs I talked about for REACH. And mainly the one to concentrate here is our version of the hybrid system here. Essentially, we just have a compressor, state 2, warm compressed air as it comes, or state 1, warm compressed air comes to state 2. And then we enter the fuel cell stack. And essentially, we're integrating a solid oxide fuel cell with a combustor. And the anode off gas, which anode fuel comes through the fuel cell and out, the anode off gas is reacting directly with the compressed air to preheat the air going in the fuel cell so that we can directly control the cathode inlet temperature of the fuel cell. Because the most important thing for a fuel cell operation is to operate at its most efficient temperature and ideally isothermal. So you want constant temperature throughout and to maintain high efficiency within the fuel cell. So that's very challenging when this inlet temperature here can change by as much as 60 degrees Celsius. So after that, back to your typical hybrid system. The hot air just goes into the turbine and then it gets exhausted out. You will notice there's no heat exchangers in this system. We also don't have any valves in this system except for a fuel valve. And we can independently operate these SOC combustion modules thermally and thermally. And so if we ever lose one, we have some redundancy and reliability. So this is a new concept. It's never been demonstrated with a gas turbine, but this fuel cells have been demonstrated in this form and fashion with this type of operation. And so this simplifies it. We also have direct reforming or internal reformation occurring inside the fuel cell stack. So we don't have to handle that, that extra component. So the idea of this system was we're trading a little bit of efficiency for power density, because in aerospace application, weight dominates. And so we have to get everything as lightweight as possible. And in this case, it was mentioned earlier, liquid natural gas. It's a great fuel for solid oxide fuel cells. And in this case, we're using bio LNG, but you could utilize natural gas, liquid methane, or even hydrogen for this type of system, because we have the ability to control the cathode inlet temperature rapidly through perturbations that this system may undergo. And just to kind of sidetrack a little bit, we're using the liquid natural gas to cool the electric motors, electronic drive, power management system, and all the other vehicle loads, including the cabin, cockpit, and other electronics, avionics, and other parts of the even engine oil. So we're picking up all this waste heat. We're providing a service to the aircraft. We're increasing the power density of electric motors by having cryogenically operated electric motors, and dramatically reducing the size of these components for an aircraft application. So I didn't have much time to prepare, only had a few minutes today to prepare this presentation. So I just kind of went on provide some simulations that we did, that I dug up from, oh gosh, maybe 5, 6 years ago, of simulating a system almost identical to the one I showed you, and how it would operate in a just a notional flight profile that we put together. So what I show here is essentially how we're powering the system, and then as also what is the altitude that the system is operating in. So this system is going from 101 kilopascals to 23 kilopascals at 35,000 feet. And if I remember my temperatures correctly, I think you're going from 15 degrees Celsius up to, I think it's around -40 degrees Celsius or so. So dramatic changes coming into that compressor inlet temperature. And then we're ramping up at time zero. We're at standard conditions, 15 degrees C, the fuel cell, everything. So we're doing a warm-up cycle, and then we're doing a loading cycle, pre-charging any batteries we may have before we take off and go on our lovely flight. And here's just a simulation of the stack warm up within 15 minutes. So we're able to basically increase the temperature. This is basically charting the maximum and minimum temperature throughout the stack. This is a one-dimensional model. So we're tracking the reformation, the temperature, and all the species and current density distributed through the model itself. I didn't have all those figures ready to go, so I'm only able to provide these. But within 15 minutes, we're able to start loading the stack. And at that point, we can kind of start still heating the stack through loading and resistive losses. And then essentially right at 25 minutes, we are stabilizing our temperature, and we're able to apply full load and on the system. And as you see here, basically this is the VI curve of how the voltage and current would change. And as we start pulling current here, exactly 900 seconds, 1500 minutes into a full load within the system. So this is, again, a plot of the temperature throughout the whole flight. Now, remember, this is changing altitude quite a bit. So around 3,000 seconds here, we're changing pressure, altitude, load, everything that we could throw at the system, we're doing it. And so we're maintaining a pretty good temperature control throughout the entire flight, or at least the perturbation parts of the flight. And with that, that's all due to we've minimized the thermal mass in the system, and we've basically have gotten direct control of the cathode inlet temperature, so we can maintain good thermal management of the SOC itself. And I just kind of show here, this is the voltage and current throughout the flight. Really just kind of after here, it's just constant. We're just mainly doing that to show how long of a flight, simulate through this and fuel burn and such. But one thing I'll notice is, there is some of the temperature feedback into the system. As you can see here, there is a little bit of a voltage rise right here. And this is due to the slow thermal response of the fuel cell. And so this is very important, the dynamics everyone's talked about, the different time constants, the gas turbines on a time constants of seconds. Some of your pressure dynamics and other things are on a time constants of milliseconds, hundreds of seconds. And then we have a fuel cell that's on minutes. And so you have to balance all these different time constants with the system, and that's in order to handle and reject these perturbations that the system undergoes and have a safe operation, high performance throughout your whole flight profile. So really this voltage elevation right here is just because the temperatures are a little bit elevated. There's a lot less resistive losses and lower losses within the fuel cell. Here I just kind of give again, this is a repeat of the previous chart, but just kind of show the voltage and currents. And this is kind of showing the efficiency of the system as we're warming up, and then we go through loading in our flight profile, and what is our overall percent power of the SOC. And you see we've made a pretty big power jump, roughly around 30% power drop in the SOC, and it was able to handle it quite well. And plus some of the other ones. So this system's able to dynamically respond to these perturbations and load and inlet conditions. And there are some spikes in efficiencies. This is just because of the thermal storage in the fuel cell. So the gas turbine is able to capitalize on some of that thermal storage to continue producing heat or producing power from the heat while the system reaches a new equilibrium. So real quick, that's kind of all the data I had to show that I could show right now. Because we're working on some of these projects for, again, Department of Energy through some of the RPE programs, and even some of the Department of Defense programs we have. We're looking at SOCs for space power systems, and also for possible aircraft or military-based aircraft and some other applications. But one thing I want to kind of summarize real quickly that I jotted down, these hybrid systems can be designed to operate dynamically in a load following regime. So it can go from minutes to possibly seconds if you are able to simplify the system and reduce some of the thermal mass of the system, so you can have the ability to adapt quickly. This does take a little bit of efficiency hit because you're not recuperating some of that heat out of the turbine exhaust. Just to give you a little bit of an estimate, if I were to increase the inlet temperature from the compressor by 100 degrees Celsius with a recuperator, that would add about 4% to this system. So you have to do the trade on, is that mass worth it? In this application, it was the density was the efficiency was high enough. It was not worth the actual extra mass that you would put that would offset fuel storage. So we have demonstrated this through simulation. We have some plans to demonstrate some of this transient response with hardware, hopefully through phase 2 of our RPE reach. And then the SOC also can go through a rapid startup. And this has been demonstrated through simulation and demonstrated through stacks out in the field and stack technologies that are currently out there. And we're basically piggybacking on that expertise and that knowledge and with our partners into this program and utilize it in this application. And so the reduction of these system components will also reduce the mass, but also help reduce cost and maintenance, so that some of these devices and components don't have to go thermal cycling throughout a profile of operation. Just like to thank you again for this time, and this is my acknowledgments to my partners and sponsors, RPE, Department of Energy, even from AFRL, Aerospace Systems Directorate, Space Command, and some of the other universities and industry partners we have.
All right, thanks so much, Rory. I know Professor Brower has something that came up, so I'm just gonna take over because I'm just gonna boss you that way. So thanks for the presentation. There's a question. I'll tell you what. Luca, can you go ahead and just unmute yourself and ask the question in the chat?
Hi, Dave.
Hi, Luca.
Hello, Rory. I wanted to ask, since from the layout you showed, I understand that the temperature at the inlet of your fuel cell changes very quickly compared to a traditional layout. So I was wondering if you are worried about excessive temperature gradients between the inlet and the outlet of your cell?
No, by controlling the inlet coming in, we're able to hopefully reduce the gradients the fuel cell will have to undergo through changes in loading and such. So this allows you, you can have some predictive controllers or whatever it may be to understand what the perturbation and how that's going to impact your temperature profile in the fuel cell. And therefore, you can actually control that temperature more rapidly. Versus
okay, so it's something you would monitor. Okay.
Yeah.
Thank you.
So Rory, I'd have a quick question for you. So in terms of, because in these aviation applications, some of your transients are pretty severe. Is there a way for your turbine to take up some of that load? I mean, in terms of how fast it responds, or do you feel like the hybrid system itself can respond really fast?
I believe at least through simulation, it's all simulation now. And not even through stack, we haven't got through stack component testing, but I believe the hybrid system itself without co-combustion with the gas turbine can actually respond very quickly, but definitely you can increase the magnitude of your response possibly through a combustion process, assisting and increasing the turbine inlet temperature of the gas turbine to be able to shift some of that load over to the gas turbine. So that is something else that can help benefit. It also helps in this case for power density. So during takeoff and some other scenarios, that also provides benefit in a transportation standpoint.
Emergency thanks. Well. And as Professor Brower mentioned in his presentation, that could be really important for stationary power generation in terms of increasing the amount of renewables that we can put on the grid, if we can make systems that respond quickly. So thanks, I appreciate it. And are there any other questions? I know that usually we try to save the questions for the end, but we seem to be running out of time. So anybody who's got a question, please feel free to interrupt. I'll give you like that 5 seconds of silence to click on that unmute button. It's really hard to find. Okay. All right, Rory, thanks so much for your presentation. And so next, we're going to turn the floor over to Dr. Biao Zhang, who's working at NETL here in the lab. And he's been working on doing rapid transients in stationary power systems. So yeah, with that, if you could go ahead and take it away.
Hello, can you see my screen?
We can see your screen and we can hear you.
Okay, perfect. Hi everyone, my name is Biao. Today I'm going to talk about our latest research about the rapid load response of solid oxide fuel cell gas turbine hybrid systems to grid demand. And we also have Dr. Haran, Mr. Rupen, Dr. Bayham, Dr. Tucker, and Dr. Manoni in the team. This is my disclaimer. And wind and solar power are variable and non-dispatchable. And because of that, they are not aligned with daily grid demand curve. As more and more renewables are added to the grid, rapid load transition is essential requirement for integrated energy system to maintain grid resiliency. And the benefits of integrated solid oxide fuel cell gas turbine hybrid system is they can provide like high efficiency, which is also equivalent to low carbon emission over a broad range of turn down, as Jack just mentioned. This hybrid cycle can reach 70% efficiency and only produce 0.3 tons CO2 emission per megawatt hour. That's a quarter as compared with conventional coal generator. And also, as Jack mentioned, from the viewpoint of grid resiliency, demand response solid oxide fuel cell gas turbine hybrid system, it can also reduce the capacity requirements for the energy storage batteries and the electrolyzers, as well as the frequency and the depth of their load cycling for extended lifetime and lower operation risk. To investigate the load response of SOFC GT hybrid system to grid demand, we have established a co-simulation platform between NETL and the Idaho National Lab, which connects the cyber-physical SOFC GT research facility, which also known as HYPER, to the grid simulation capability at INL. The longer-term vision of this test capability is to also involve the renewable generation assets at NREL to evaluate the actual variation of renewables and or together accelerate the development of load responsive hybrid system to catalyze the transition to net zero carbon power generation. And as shown in the right part of these figures, the HYPER facility is a cyber physical platform which couples a high fidelity real-time SOFC model together with real hardware and a virtual power electronic interface model. So it can faithfully represent the dynamics of a real SOFC GT system. Our goal for this study is to achieve 50% turn down and the following ramp up in 10 seconds. So in order to do that, we ramped the fuel cell and turbine load concurrently. And we also manipulate the fuel cell anode fuel valve so that its opening is proportional to the fuel cell current load. The purpose here is to maintain the fuel cell fuel utilization at about 65% to avoid the fuel starvation in the fuel cell or the overpotential at the turbine inlet. And meanwhile, since the oxygen consumption and cooling demand for the fuel cell reduced at turn down conditions, the cathode airflow was reduced by opening the hardware bypass valve here from 25% to 100%. So a large amount of heated air can be bypassed from the fuel cell stack. And in this way, we can reduce the air entered the fuel cell stack. Lastly, we used a pre-combustor after the recuperator. The pre-combustor is here. We used it to further increase the cathode inlet air temperature and also serve as a control knob. So for load transitions, the fuel to this pre-combustor is also manipulated with the aim to maintain the cathode inlet air temperature. And this is our experimental results. So NUDIP's group at INL sent us grid demand signals from their grid simulator. And NETL's HYPER facility successfully load followed to the grid demand. We demonstrated here about 50% load turn down, and the following ramp up can be achieved in 10 seconds. And this two figure shows the measured air mass flow, temperature pressures we measured from the hardware, and we used these three air parameters as a primary input to the cyber physical fuel cell model. So as you can see here, the pressure did not change for both the turn down and the ramp up case because we used the PID speed controller to maintain the turbine speed. So we keep the turbine speed constant. And for the turn down case, As the hot air bypass valve opened from 25% to 100%, our airflow rate dropped from like about 1 kilogram per second to 0.5 kilogram per second. And during this 10 seconds load transition, we can see the air temperature did not change much, only 3 degrees C. But after this load transition, for the next 110 seconds, this air temperature dropped significantly, about 51 degrees C. This is because at that time, our turbine is working at half load, which is 25 kilowatt, so less heat can be recovered from the recuperator. That's why you can see this temperature drop. And this transient points to the coupling effect of SOFC-GT system, and also highlighted the value of hardware-based simulation. The same similar situation is observed for the ramp-up case. We also found like the cathode inlet air temperature is critical for fuel cell thermal management during this rapid load transitions. This figure shows like during the load change, the cathode inlet temperature was relatively steady, but during the 10 seconds load change, it showed like a 40-degree surge and then dropped to the desired target. And the reason is showed in the right figures. So as you can see from the bottom figure here, so both the air temperature and the pressure was nearly constant during this 10-second time window, suggest like they have minimum impact at the cathode inlet air temperature, but both the air mass flow and the pre-combustor fuel mass flow, they dropped linearly. Although like they dropped linearly, but the cathode inlet air temperature actually showed nonlinear behavior in response. At the start of the ramp, the cathode airflow was slow to response. So there is a gap between our like command to the hardware and their actual response. The gap is about 1.2 seconds. This behavior like reflects the real actual transients you can expect from the real hardware. And the pre-combustor used in this study is a virtual component, which showed a linear ramp. So this net result is our fuel flow ramped initially, leading this air mass flow change. And that's why they caused this initial temperature drop. And then the air mass flow changed more rapidly as compared with the pre-combustor fuel. That's why you can see this surge. And at the end of this 10-second ramping, they back to alignment, and the cathode inlet air temperature returned to the desired target. Again, like similar result was found for the ramp-up case, so I didn't show it here. And this study clearly shows nonlinearities, which is not commonly captured in model-based studies, can be well captured in our hardware-based experiment. Right? And our data also suggests the fuel cell was thermally protected during rapid load transitions. The solid temperature difference is between node number 1 at the inlet and node number 12 at the outlet can be used as an indicator to estimate the internal fuel cell temperature distributions. As you can see, for both the turn down and ramp up case, the solid temperature difference is well below 120 degrees C, which is a threshold suggested by many industrial partners. And the two figure at the bottom, we show the local temperature gradients. As you can see, like higher low temperature gradient was observed for the front end of the cell, for example, on nodes 2, 3, and 4. because like most of the electrochemistry happens there. And the more important thing here is for water nodes, we found that like the local temperature gradient was lower than the 10 degrees C per centimeters, which is also a threshold like recommended by our partners. Below this, the temperature, we will not see like very obvious degradation for the fuel cell stack. And this is further confirmation like our fuel cell was thermally protected during this rapid load change. Again, fuel cell stack, SOFC can not only suffer from temperature stress, thermal stress, but also suffer from electrochemical degradation at unfavorable fuel distribution, especially for the ramp-up case. And this figure shows the instantaneous fuel utilization curve during load transitions. In general, our strategy worked well. Keep the fuel cell fuel utilization well below 70% during the load transition, but we also noticed some non-linearity here. That's because to represent a real fuel cell stack, the fuel cell anode fuel was regulated by fuel valve models. And although our valve opening was proportional to the fuel cell current load, the actual fuel mass flow was not proportional to the valve opening, and that's why it caused this nonlinear transient. And this figure shows the overpotential on the fuel cell nodes. Here I only took the overpotentials on nodes 1, for example. This figure suggests like for the 3 overpotentials, the last one, diffusion overpotential, was much lower than the activation and ohmic overpotential, which suggests the fuel transfer limitations can be negligible during this rapid load transitions. So we believe like based on all this experimental data we showed above, the fuel cell was protected during this rapid load transition without violating operability constraints. And perspective here is in the past years, fuel cells were mainly considered as large base load system. However, given the current driving force towards net zero low carbon emission power sector by 2035, there could be a paradigm shift for the intended application of fuel cells from large base load to flexible load responsible systems in order to maintain the grid resilience. I think we believe our current demonstrations suggest like SOFC GT hybrid have the potential to meet the load responsible demands of this new paradigm. And our data results showed here clearly suggest like the nonlinear coupling of the system components, which points to the need for the development of adaptive controls. We are working on that, and our future step is to do a full system characterization and develop adaptive controls, so we can automate the load transition control of our system to provide better grid response and even grid service. So that's my presentation. Thanks.
All right, thanks, Dr. Zhang. Are there any questions for Biao? Well, let's see. Okay. If not, we have another presenter, a student, and as you all know, we love students. So, is it Carlo Alberto was presenting? Are you online, Carlo?
Yes, I'm here. Can you hear me?
Yep, I can hear you.
Perfect. I will share my screen. Hopefully you will see it in a few seconds. So, okay. Just 1 second that I had some connection problems, but I hope now you will see. Are you seeing it?
Okay, so
you can see it, okay? So
I can see it okay, Carlo, but understand we don't have a lot of time. So
yeah, I will start in a few seconds. So my presentation is about incipient surge detection.
So Carlo, before you start, you'll have to introduce yourself because I don't have information on you. So.
Exactly, yes. In this first slide, I try to present myself, and I'm a PhD student at the University of Genoa.
So Carlo, sorry to keep interrupting, but we can't see. All we see is a gray screen right now.
Okay, but okay, so you are not seeing it. Why?
Okay,
Sorry.
I can see your PowerPoint.
Okay.
But when you go to presentation mode, I can't see it.
Okay, so I can leave it like here, like this.
Okay. All right, sure, no problem. We're flexible.
Okay.
Go ahead.
So I'm a PhD student at the University of Genoa. I'm the third year PhD candidate, so I'm finishing my PhD. And my supervisors are Prof. Silvestri and Professor Massardo. And I will show you just a brief overview about the incipient surge detection activity that we are conducting at the University of Genoa. This is important in the energy field because, as you know, of course, it's important to deal with large volume energy systems in hybridization process. And so surge detection becomes important because when we are going to put bigger volumes downstream of the dynamic compressor, we can increase the surge risk in power plants. So, for example, here in Genoa, we have a test rig, which is a night temperature fuel cell emulator. So a fuel cells hybrid system emulator, which is made up of many modular vessels that can be put downstream of the compressor to emulate the fuel cell, for example, solid oxide fuel cells in hybrid systems. So what we performed here is an activity based on vibroacoustic measurements. And for example, here, I hope you can see at least my cursor. Here we have an example of accelerometer signal detected on the compressor. So it was placed on the compressor. And here an example of tachometer. So this is a rotational speed acquired signal during a surge transient. So you can see that when we go, of course, towards instability, so the plant is working in a nominal conditions, so in stable working conditions. When we go towards instability, so on the compressor map, we approach the surge line, then we increase, we experiment, the compressor undergoes also fluctuations in his angular speed, as you can see from this plot, experimental plot. And this is part of the instability that, of course, we don't want to take place in our energy system. So what we did in brief was to post-process a lot of experimental data that we acquired. And for example, starting from the classical power spectrum, which are conventional processing techniques, we performed the fast Fourier transform, both on microphone and accelerometer signals acquired. And we, in the frequency domain, as you can see, we obtain some energy peaks which are not present in the stable conditions, which are acquired far from surge conditions, while in surge transients we can detect some subsynchronous spectral content, that is at a frequency which is lower than the rotational speed of the machine, that is around 1 kilohertz, as you can see from these peaks in these spectral plots, these frequency plots. So this could be a surge precursor because it could be ascribable to vaneless diffuser rotating stall, because in this case we have a vaneless diffuser in our dynamic compressor. What we did here also, it's a high frequency range analysis, because we think that approaching surge conditions, the energy of the blade pass frequency can be affected by this phenomenon. In particular, we think that it can be affected by rotating stall inception. And as you can see, passing from stable, again, from stable functioning to surge condition, we can see that the energy of this frequency contents decreases. So with respect to the stable condition, we have less energy in the blade pass frequency and in his first harmonic, which is the most energy, characterized by the higher energy, in this case, the highest energy. So also this could be another surge precursor. So at the end, we performed also cross correlations between the two different sensors to see if there are common spectral contents, and we found again this subsynchronous common content, frequency content, that is not present in a stable condition. And this was made also again in the high frequency. So also when cross correlate, in this case we are examining the cross power spectrum between microphone and accelerometer, and also in the high frequency we observed the same trend that I've showed you in the previous slides. So we consider that this could be interesting surge precursors that could be implemented in a control system, in a real-time control system for surge avoidance, for early surge detection. I will just go very quick. Here I can show you some time frequency analysis, which are a bit different from the classical Fourier transform that I showed you before. So in these plots, we can see the time which is passing and the frequency, and we can observe a lot of, let's say, of physical phenomena which take place. For example, here you can see the speed that is changing, that is analogous to the plot I showed you before, and also you can see what happens passing from stable condition going towards surge. This can be compared to a stable functioning again, as we did previously, and this can be another useful tool to detect some surge precursors, because here in this case we compared also different plant configuration with different interposed volumes downstream of the compressor, and we observed always this frequency content that you can see is constant in the time before surge occurs. Then when surge occurs, it loses its energy and can be ascribable to vaneless diffuser rotating stall, we think. And this happened to for let's say all the configuration with the different volumes tested. So we think it could be a robust surge precursor. In the end, here again, the high frequency analysis that I showed you before, you can see also with the time. In this case, in the stable functioning, we have the blade pass frequency, which is has more and seems to be more energy than in the case of surge transient. So again, this could be an indicator or a revealer of surge instability that is going to take place. And finally, very shortly, a last slide where we performed a simple calculation of the auto-B spectrum, which is again similar to those plots I showed you before, but with two frequencies on the main axis. So this auto-B spectrum is useful because we built an indicator, quantitative indicator, and we defined it as the sum of all the spectral contents in the subsynchronous frequency range, because we think that is typical of the instability that occurs before surge happens. And we compared this indicator for all the probes, so accelerometer, microphone, and also for an accelerometer that was placed on the compressor housing. And we obtained that in all the cases, this indicator is robust because it reveals, it gives a higher value when approaching instability conditions related to surge risk in power plants. So I hope it was good with the time, and if you have a question, I will be glad to answer.
No, thank you so much, Carlo. We really appreciate it. It's a lot of complex stuff to talk about in just 10 minutes, but you did a good job. So
yeah, it was just to show you an overview, and that we could have many surge precursors that we can use to to avoid surge and to control even hybrid system complex plants.
Okay, so so yeah, any questions?
Okay.
And if not, thank you, Carlo.
Thank you.
And plus, of course, you can. Like there's a discussion I noticed going on between Professor Roberts and Dr. Pizzini in the chat. So just you can send a message to Carlo, who'd be happy to answer, I'm sure.
Okay, of course. Okay.
And so I'll just go ahead and finish up. I have, I guess I do have a final presentation, which I really wanted to, so mine is only like, it should only be 4 slides, so I'll have to go through quickly. But Nana, do you see my presentation, or is it in?
Yes, I can see.
Okay, all right, good. It's hard to tell because I also have too many screens. All right. So yeah, I wanted to talk real quick about the opportunity and challenges for SOFC gas turbine hybrid dynamics. Of course, there's a lot of work in this area, but again, I wanted to stimulate some ideas for discussion, and perhaps this is discussions offline. We did some work. Again, this comes from work that Dr. Noorfrida Haroon did in her dissertation work, showing that you could get when you change the fuel composition, you could get these extreme transients, which at first was a really big problem, but then it turned out that we could also use this for mitigating other transients, right, if we matched it up. And it also gave us an opportunity then to take a look at locating the reformer. Instead of doing on-anode reforming or doing pre-reforming, we could put the reformer still before the anode, but we could derive that heat from heat coming out of the post-combustor of the fuel cell system. So I know Carlo just talked about compressor surge install, so that's worth a couple of points. We found that there are you can bypass. So bleed air is a more common way to buy surge margin. These are startup profiles. You can see that as you increase the bleed air, you go further away from the stall line. This is a compressor map. So pressure ratio versus corrected airflow, and as you open more bleed air, you get more things. Of course, you use more fuel, but bypassing airflow from the compressor to the turbine inlet, which also bypasses the pressure loss in the system, also can buy you a lot of surge margin. And that would be like a control strategy that you would use. So this is just showing that we did this to demonstrate that it's the dynamic actuation of the cold air pulls you away. So this is the startup here. We get up to our operating condition here, and then we open the valve. You see it pulls us away from the stall line, and then when we close it, it pushes us back towards the stall line. Here, I just wanted to show a compressor stall, and we can see that this is definitely results in damage, because you can see that these are really big swings in the compressor volume. Even the speed is changing a lot in a short period of time. And this is the stall line, and this is how you can see what's happening during the compressor stall. This is in response to hitting an emergency shutdown button. So which we've changed that strategy. But you can see big chunks missing out of our compressor. And so that's a very unhappy thing. And finally, just to say on a more positive note, in degradation, we found that there are this is a dynamic or a transient that we want to deal with, but we found that there are operational modes, different control strategies that we can use to extend the life of the fuel cell by a significant amount. As Rick pointed out in the very first session of the day, we could extend the life by 7 to 10 times, which does have a significant impact on your internal rate of return or your net present value. So that's it. For me. Is there any? Let's see. I need to stop sharing. Okay, and then I can take a look in the chat. Okay, so Rory, maybe you could just go ahead and unmute yourself.
I was just curious what your sample time, when you showed that surge, You know, what was your sample time? Did you actually capture the RPM peak?
So, yeah, so our sample time was 200 hertz, so 5 millisecond time steps.
Oh, wow.
Yeah, so we did. Now, we've had surges where I'm not sure that we did capture the peak even with 200 hertz sampling time. So, but yeah, it's definitely devastating on the turbine. I've destroyed. Oh, I shouldn't say that. Okay, I'll just say that over the course of 20 years, we have had, we've been hard on 5 turbines that had to be replaced. Let's just put it that way, which is not so bad because we're talking a 20-year period, right? So, but we've learned a lot about surge and stall. So, needless to say, we're very excited about Carlos and Professor Silvestri's research, hoping that we can test out some way to detect surge and stall before it happens and automate a process to keep that from happening. So, does anybody else have any other questions? I know that we're kind of at the end here, and it's been a long day. So, I'm just going to say tomorrow we start off with some of the RPE stuff that Rory had talked about. Dr. David Tu will be hosting a session where they'll have participants from both the Integrate program and the REACH program talking about commercializing hybrid technology. That'll be followed by a session on controls. We've heard a lot about controls over the last couple of days, and so Dr. Paolo Pizzini will be leading a session on controls specifically applied to these hybrid systems, trying to overcome some of their difficulties. And then finally, we'll just wrap everything up and try to summarize what we think are the most important points. So I invite all of you to please attend the very last session and give us your comments. We're going to, whether you want to do it in the chat or whether you want to unmute yourself and talk about it, we'll have an hour and a half session to wrap everything up and try to capture everybody's ideas. Okay, with that, I thank everyone so much for your attention and being part of the sessions today. And have a great evening, night, morning, whatever it is for you there. So thank you very much.